Hello there, and welcome once again to Science for Sleep, the little corner where curiosity settles into a slower rhythm and knowledge becomes something you can rest beside. Tonight we'll be lifting our eyes to the quiet of the night sky, that velvet stretch above us that has carried human imagination for as long as people have walked the earth. And though it is sprinkled with stars, constellations, and passing hints of motion, tonight there is a single neighbour we'll be leaning toward, a galaxy so vast that even the word enormous feels inadequate, and yet it is also so close that with nothing more than your own eyes, on a clear enough night, you can actually see it, the Andromeda Galaxy. It waits in silence, drifting just above the horizon of thought, and we're going to spend a long while together tonight trying to understand what it means when we ask, how big is Andromeda really? Take a moment if you can to imagine where you are right now. Maybe you're tucked under the covers with the lights already low, or maybe you're listening from a favourite chair in the quiet of evening. Wherever you are, the sky above you, though separated by time zones and weather and all the turns of the Earth, is the same sky that has always been there, the same one that carries the faint glow of Andromeda. In fact, you might already have seen it, perhaps without realising. To the naked eye it appears as a smudge of light, a dim blur just beyond the constellation of Andromeda herself. Nothing flashy, nothing demanding attention. It doesn't sparkle or twinkle the way bright stars do. Instead, it hangs almost shyly, as if it knows that those who notice it will pause a little longer, squint a little deeper, and in doing so will join a tradition that stretches back across thousands of years. Before we settle further into that thought, I want to ask you something simple, just as a way of anchoring us in the moment. Where are you listening from right now, and what kind of night is it where you are? Is the sky clear above you, or is it hidden behind clouds? Is it early in the evening, the day still fading, or is it well past midnight, the quiet hour when the world slows to a hush? Asking you this isn't about time zones or geography alone. It's a gentle reminder that we're all sharing this conversation at once, even though our clocks and our skies might not match. Somewhere it is already morning, somewhere else the moon might be high, and still, here we are, speaking together about a galaxy that is as real to you as it is to me, a galaxy that shines with a light so old that it began its journey before humans had written a single word. Now, if you find these moments soothing, if you enjoy drifting into sleep with a soft kind of science by your side, I'd be so grateful if you gently tapped the like button, or perhaps subscribed, so that this little corner of calm can find others who might need it too. Just as stars scatter across the night sky, these small acts scatter comfort across the world, and that feels like something worth doing. So let's ease forward. Andromeda. It is both familiar and mysterious, a galaxy that has been painted in countless photographs and charts, but also one that hides behind the sheer scale of what it actually is. When we say galaxy, we mean a collection of hundreds of billions of stars, along with clouds of gas, fields of dust, invisible halos of dark matter, and a restless central core where even gravity seems to bend in on itself. Andromeda has all of that, and more. It stretches across the sky with a span so wide that if your eyes were sensitive enough to gather its full glow, it would appear many times larger than the full moon. Instead, our eyes only catch the brightest parts, leaving it to telescopes and careful observation to reveal the full enormity. To ask how big it is means more than one thing. Do we measure its width, the distance from one edge of its spiral arm to another? Do we measure the number of stars that fill it, each one with its own size, its own possible planets, its own possible stories? Do we measure the invisible weight of the dark matter cocoon that surrounds it, shaping its gravity in ways we can feel but not see? Or do we measure its importance to us as the closest spiral galaxy to our own, a neighbour so near that our destinies are already tied together by gravity? Big, in the case of Andromeda, is not just about kilometres or light years. It is about perspective, about stretching human imagination into forms that almost resist comprehension. If you close your eyes and think of the word big, maybe you picture a mountain range or the endless surface of an ocean. Maybe you think of a city skyline, or even the span of the Earth itself as seen from the edge of space. Andromeda is larger than all of those things, larger than any single comparison can hold. It is not just big in the way one object is larger than another. It is big in the sense that it contains multitudes, billions of suns, and the energy and matter of countless systems. To fit that into a single thought is difficult, and yet that is where our journey tonight begins. Imagine standing beneath a dark enough sky that the glow of human cities is far behind you. The stars spill out above, sharper, brighter, more numerous than you're used to seeing. In that darker canvas, the faint oval of Andromeda appears. Not a star, not a planet, but something more diffuse, almost ghostly. You know that what you're looking at isn't a point of light, but an entire galaxy, one so large that your eyes can only gather the tiniest piece of it. That hazy blur is the combined glow of hundreds of billions of stars, each one too faint to be seen individually from here, but together forming a collective shimmer that reaches across 2.5 million light-years of space. 2.5 million light-years. It's a number that almost slides past without sticking, because our minds are not built to hold scales like that. A single light-year is the distance light travels in a year, nearly 10 trillion kilometers. Multiply that by 2.5 million, and you begin to sense the gulf. And yet, that gulf is small compared to the stretches that separate us from most other galaxies. Andromeda is close enough that it is part of what astronomers call the local group, a small neighborhood in cosmic terms, and that nearness makes it both a subject of fascination and a reminder of how vast the universe really is. What you see with your eyes when you look at that faint smudge is only the central brightness, the crowded hub of the galaxy where stars are densely packed. Spread out around it, invisible without assistance, are spiral arms that arc outward for hundreds of thousands of light-years. They contain younger stars, pockets of gas where new stars are forming, and lanes of dust that ripple like shadows through the starlight. If our eyes were tuned differently, if we could see across the spectrum into ultraviolet or infrared, Andromeda would appear even more intricate, with tendrils of structure reaching far beyond what we imagine when we say the word galaxy. And still, in the quiet of night, to us it is a blur and a question. How big is it really? That is what we will unravel together, not in a hurry, not in a rush of numbers, but slowly, steadily, with room for wonder, with room for reflection, and with room for the simple comfort of knowing that even as we talk about galaxies, the purpose here is as much about sleep as it is about science. When you first hear about the Andromeda Galaxy, it might sound like something distant and unreachable, a grand name reserved for astronomers with powerful instruments and long nights of observation. But in truth, Andromeda is one of the few galaxies you can meet with your own eyes, a neighbour that requires nothing more than a clear sky and a little patience. This makes it unusual. Most galaxies are far too faint, their light dispersed across space until it slips beneath the threshold of human vision. Andromeda is different. It is close enough and bright enough that if you know where to look, you can see it as a pale patch hanging above the horizon, a reminder that even without telescopes, our ancestors had a direct connection to the larger universe. Think about that for a moment. For most of human history, the night sky was not just a background, but the most constant presence in daily life. Farmers read the seasons in its patterns, sailors navigated by its markers, storytellers wove myths into its constellations, and woven into those same constellations was Andromeda, not as a galaxy. That word didn't exist yet, but as a faint, curious glow. Early observers gave it names tied to their myths and constellations, but what they all shared was a recognition that this little blur was unusual. It didn't behave like a star. It didn't have the sharpness of a planet. It was something else, something larger, though they couldn't yet know how much larger. If you try to find Andromeda yourself, the best way is to first find the constellation Pegasus, with its great square, and then trace a line from there to the figure of Andromeda, the mythological princess chained to a rock in ancient Greek tales. Just off to one side of her constellation lies that soft oval glow. To the naked eye it is modest, nothing more than a smudge. Through binoculars it becomes more distinct, revealing a stretched ellipse, and with a telescope the spiral shape begins to emerge, a structure of arms and dust lanes that stretch out like whirlpools. But no matter how you view it, what you're looking at is a galaxy more than twice the size of our own Milky Way, seen from across millions of light years. That hazy patch you glimpse is already light that began its journey long ago. The photons reaching your eyes left Andromeda about 2.5 million years ago, back when early humans on Earth were still shaping stone tools, long before civilization, long before cities, long before we knew how to look at the stars with instruments. The Andromeda you see is, in a very real sense, a time capsule. By looking up, you are looking back. You are seeing not what Andromeda is tonight, but what it was millions of years ago, and every night you see it, the image you catch is that same ancient message arriving fresh at your eyes. Astronomers have often marvelled at this quality of light, the way it allows us to read the past written across space. With Andromeda, it is especially striking because the galaxy is close enough to be visible, but far enough that we are still peering into a prehistoric chapter of its story. This alone makes it feel enormous. To think that your unaided eyes are catching photons that travelled unbroken across millions of years and landed here tonight, in this moment where you are listening, where I am speaking, where countless others are going about their own evenings, that is not just a number. It is a meeting between human scale and galactic scale, something rare and humbling. If we step back and imagine Andromeda as it truly is, we realise how deceptive that faint glow can be. The light you see is concentrated in its dense central bulge, but the galaxy extends far wider. If its full disk were bright enough for human eyes, it would cover a portion of the sky wider than the moon, several times over. Imagine looking up and seeing a spiral galaxy stretched across the heavens with arms spanning out as if to embrace the entire dome above you. That is what Andromeda actually looks like, but our vision only gathers its core. In that sense, meeting it is like greeting someone in dim light and only seeing their silhouette. You know they are there, you sense their presence, but the details are hidden until you adjust your view. This is where instruments step in. With binoculars, you begin to see more shape, with telescopes more structure. With long exposure photography, the galaxy reveals itself in astonishing colour. Blues where young stars burn hot, yellows where older stars gather, dark lanes where dust obscures the starlight, and faint wisps where the spiral arms trail away into the intergalactic medium. Each method of looking reveals a little more of what Andromeda truly is. But the simplest method, the human eye glancing upward on a clear night, remains the most profound, because it connects you not only to the galaxy, but to the countless people across history who looked at that same blur and wondered. Consider those people for a moment. Ancient Greek astronomers noticed it. Persian and Arabic scholars described it. In the 10th century, the Persian astronomer Abd al-Rahman al-Sufi wrote of a small cloud in his Book of Fixed Stars. Centuries later, European observers catalogued it as a nebula, a fuzzy patch they assumed was within our own Milky Way. It wasn't until the 20th century that Edwin Hubble measured its distance and showed that this little blur was not part of our galaxy at all, but a galaxy of its own, vast and separate. That discovery reshaped our understanding of the universe. Suddenly the cosmos wasn't just the Milky Way. It was a universe filled with galaxies, each one an island of stars, and Andromeda, the one visible to the eye, was our closest island neighbour. Meeting Andromeda in the night sky, then, is not only about spotting it, it is about standing in a line of human curiosity that stretches across millennia. It is about recognising that the same photons have been touching eyes since before history was written. It is about feeling the scale of something that dwarfs human concerns and yet invites us to be part of its story. Because Andromeda is not just a distant object, it is bound to us, gravitationally linked to the Milky Way in a slow-motion dance that will eventually bring us together in the far future. That smudge you see tonight is also a hint of where our galaxy is headed. When we ask how big it is, it helps to begin with this meeting. To recognise that size is not just about numbers on a chart, but about presence in the sky, about the reach of light across millions of years, about the way it sits in our perception as both faint and immense. Standing outside on a clear night, feeling the cool air, looking up at that blur, you're encountering something that stretches 220,000 light-years across, containing nearly 1 trillion stars, and yet all of it arrives to you as a fragile shimmer, no brighter than the faintest star nearby. That contradiction, immense reality versus humble appearance, is part of what makes Andromeda so remarkable. And so the meeting begins here, with your eyes, with the quiet recognition that a galaxy beyond our own is visible. But the story does not stop there. The more you look, the more questions arise. What are those stars made of? How far do its arms extend? How do we measure its distance? How many systems spin inside it? How many worlds might circle its stars? Each question leads deeper from the simple blur you see in the night sky to the incomprehensible structures we will try to unravel. When we talk about the Andromeda Galaxy, it's easy to let it remain a distant concept, a diagram in a book or an image pulled from a telescope. But have you ever truly seen it with your own eyes? That faint oval glow above the horizon, the patch of light so modest that many people never notice it. It can be surprising to realise that without any equipment at all, your own vision is capable of collecting the light of a galaxy 2.5 million light-years away. And yet, for many, the Andromeda Galaxy is something they have heard of but never actually sought in the sky. Maybe you have stood outside at night and noticed the constellations you know, the bright and obvious ones. Orion with his belt, the Big Dipper, Cassiopeia shaped like a bent W. These constellations pull the eye because they are clear and recognisable. Andromeda's glow is different. It is quiet. It doesn't declare itself. You have to look for it, and sometimes you even have to look slightly away from it, using the edges of your vision where your eyes are more sensitive to faint light. This technique, called averted vision, has been used by stargazers for centuries. When you finally catch it, the experience is subtle, just a blur, just a patch. And yet, knowing what it is transforms the experience entirely. You're not just looking at a faint cloud, you're seeing the combined light of hundreds of billions of stars. That moment, standing outside and finally finding Andromeda with your eyes, is often described by people as a mixture of humility and wonder. The humility comes from realizing how small your own vision is compared to the scale of what you're seeing. The wonder comes from the realization that even with that limitation, you're able to connect to something so immense. You don't need a spacecraft or $1 billion observatory. You don't need a scientific degree. All you need is darkness, a patch of clear sky, and a little patience. That accessibility is part of Andromeda's magic. If you've never had that experience yourself, imagine it. Picture yourself standing somewhere far from the wash of city lights. Maybe you are in a quiet field, or by a lake, or on a mountain where the air feels thin and crisp. The stars above are brighter than you have ever seen them. The Milky Way cuts across the sky like a faint river of light, and beside it, in the constellation of Andromeda, you notice a smudge. It looks almost like a fingerprint pressed lightly onto glass. Oval, pale, easy to miss if you don't know what to expect. You stop and stare. Your eyes adjust. Slowly, the patch becomes more obvious. That is Andromeda. That is another galaxy. That is light that has been travelling since long before modern humans walked the Earth, arriving tonight to meet your eyes. For many people, This kind of encounter feels different than seeing a photograph. A photograph can show you the galaxy in exquisite detail, with colours enhanced and structures revealed that the eye could never see. But a photograph is mediated, captured, processed, displayed on a screen. Seeing Andromeda with your own eyes is not about detail, it is about connection. You're standing under the same sky as ancient astronomers who recorded it on parchment, the same sky as travellers who used it as a point of reference, the same sky as countless humans who wondered what that faint blur might be. In that moment, you join a lineage of observers stretching back thousands of years. It can be startling to think about how many people go their whole lives without realising they can see another galaxy unaided. The night sky has become dimmer for most of us, hidden by the glow of electric lights, confined by tall buildings, blurred by pollution. But the Andromeda Galaxy is still there. Its photons are still falling on rooftops and sidewalks every clear night. They're still slipping through the atmosphere and still reaching our eyes, whether or not we notice them. To pause and actually look is to reclaim something quiet and ancient. Some describe the experience in deeply personal ways. They say it makes them feel small, but not in a way that's frightening. More in a way that relieves pressure, as if their daily concerns shrink against the backdrop of galaxies. Others say it makes them feel part of something larger, part of a universe that is active and connected, where their own existence is one thread among countless others. Some even describe it as grounding, paradoxically enough. By looking at something unimaginably distant, they feel more rooted in their own place and time. It's worth remembering that light from Andromeda doesn't arrive all at once. Every second, new photons stream across the gulf of space and fall upon Earth. That means that whenever you look, you're catching a fresh batch of travellers who began their journey millions of years ago. The light you saw last night isn't the same as the light you'll see tonight. It's all ancient, but it's continuously arriving. Meeting Andromeda with your eyes isn't a single event. It's an ongoing relationship, a constant flow of ancient signals. Now perhaps you're listening to this in a city, where light pollution drowns out all but the brightest stars. Maybe you've never seen Andromeda and wonder if you ever will. That's all right. Even if the sky above you is washed in orange or grey, Andromeda is still there. It hasn't gone anywhere. It's only hidden from your view by the conditions here on Earth. If you ever find yourself travelling to a place with darker skies, remember this conversation. Take a moment, step outside, let your eyes adjust, look up, try to find that faint blur. It may take a little patience, but the reward is worth it. Astronomers sometimes speak about galaxies in terms of numbers. They'll tell you Andromeda is about 220,000 light years across, that it contains nearly 1 trillion stars, that it is moving toward us at about 110 kilometers per second. Those numbers are real, and they're important for science. But none of them capture what it feels like to simply see the galaxy with your own vision. No number can reproduce the quiet astonishment of finding that pale oval in the dark and knowing that it's not just a smudge but an entire island universe. You don't need to be a professional astronomer to appreciate that feeling. You don't need to know the equations or the physics. The encounter is human, universal, something that anyone with eyes and curiosity can share. And perhaps that's why the question of whether you've ever seen Andromeda yourself matters. Because if you have, you know the quiet thrill of that recognition. And if you haven't, then the thought of doing so can become a goal, a small adventure waiting in the night sky. There is something grounding in realizing that the sky is full of wonders we can meet directly, without screens or devices. The Andromeda Galaxy is the grandest of these accessible wonders, a neighbour galaxy visible to the eye. To pause and seek it out is to give yourself a gift of perspective. For a few minutes you stand outside of your daily scale. You step into the scale of galaxies, and while the details may remain hidden, the sense of enormity is present all the same. Perhaps the most striking part of all this is how ordinary the experience can seem from the outside. Someone walking past you while you gaze upward might not notice anything unusual. They might think you're just staring at the stars. To them, nothing remarkable is happening. But for you, in that moment, something extraordinary is unfolding. You're connecting across millions of years and millions of light years to an entire galaxy. That's not visible from the outside. It's something felt, something known, something that transforms a faint blur into a cosmic encounter. So, I ask again, have you ever seen it with your own eyes? Have you stood under the stars and noticed that pale glow? If you have, perhaps you remember the exact night, the season, the company you were with. Maybe you remember the crispness of the air, the silence of the moment. If you haven't, then the next time you find yourself under a dark enough sky, you can carry this knowledge with you, and when you do see it, you'll know that you're looking at another galaxy, the closest great spiral to our own, a neighbour that will one day merge with us in a cosmic dance. In the end, meeting Andromeda isn't about telescopes, or charts, or even astronomy as a discipline. It's about being present in a moment of recognition. It's about letting yourself feel small and vast at once. And from that recognition, questions naturally arise. If you can see Andromeda with your eyes, what exactly are you seeing? How many stars? How far does it spread? How do we measure something of that magnitude? When you first realise that you can see an entire galaxy with your eyes, the natural question that follows is, just how big are galaxies anyway? The word itself is one we use casually, as though it were just another category of object like planet or star or comet. But galaxies are not simply larger versions of stars. They are structures so immense that it takes deliberate effort to even begin to picture them. To call them big is almost misleading, because the scale involved is not just larger than our daily lives, but larger than anything the human mind is naturally prepared to handle. Think first about our own galaxy, the Milky Way. It contains perhaps 400 billion stars. Each of those stars is, in its own right, an enormous ball of gas shining with energy for billions of years. Around many of them orbit planets, some rocky, some gaseous, some with moons of their own. The space between these stars is not empty. It is filled with dust, with gas, with radiation, with magnetic fields, with the invisible scaffolding of dark matter. All of that together forms the galaxy. And yet, despite its enormity, the Milky Way is not the largest galaxy out there. It is only average, modest compared to giants like Andromeda. When we talk about the size of Andromeda, one of the simplest measures is its diameter. The main disk of the galaxy spans roughly 220,000 light-years across. To put that in context, if you were to travel at the speed of light, the fastest speed in the universe, it would take you 220,000 years to cross from one side to the other. Remember that a single light-year is almost 10 trillion kilometers. Now multiply that by 220,000, and the numbers stop feeling like numbers at all. They blur into something the mind can no longer easily grasp. And that is only the visible part. Surrounding the disk of stars is an even larger halo of dark matter, extending perhaps 1,000,000 light-years or more, shaping the galaxy's gravity and holding it together. It helps sometimes to compare. Our entire solar system, from the sun out to the edge where comets drift in the Oort cloud, is about 2 light-years across. That is vast enough that spacecraft launched decades ago are only now approaching the boundary. Andromeda could contain that entire span not once, not 10 times, but over 100,000 times across its width. The difference in scale is so extreme that calling them both by the same kind of measurement, kilometers, light years, feels almost unfair, as if the language itself is strained by what it's being asked to describe. Another way to look at it is through the number of stars. As best we can estimate, Andromeda contains nearly 1 trillion. That is 1,000 billion. If you were to count one star every second, you would need more than 30,000 years to finish counting, and by then, new stars would have formed, and old ones would have died, so your tally would already be outdated. Each of those stars is a sun in its own right. Many of them have planetary systems. The sheer number of possible worlds contained within one galaxy is staggering. and Andromeda is just one of hundreds of billions of galaxies in the observable universe. This is where the immensity of scale begins to overwhelm. When we talk about Andromeda, it is not just an isolated object, it is part of a hierarchy. Within it are stars and planets, clustered into systems. Those systems are grouped into spiral arms. Those arms form part of the galaxy. The galaxy belongs to the local group, a collection of about 50 galaxies bound together by gravity. The local group itself is part of the Virgo supercluster, which in turn is part of an even larger web of superclusters stretching across the observable universe. The scale expands outward in layer upon layer, each one dwarfing the one before it. And yet, here we are, trying to hold it all in thought, starting from that faint blur we can see in the night sky. It can help to anchor these numbers in something more familiar. Imagine the Earth as a single grain of sand. Now imagine that every grain of sand on every beach on Earth is a star. Even that comparison is not enough to capture the number of stars in Andromeda. And then remember that Andromeda is only one galaxy. The immensity is not just in the size of one structure, but in the realization that such structures are common. What feels extraordinary to us is, in the context of the universe, ordinary. Galaxies like Andromeda are scattered throughout space, each one vast, each one containing billions or trillions of stars. When astronomers try to describe these scales, they often rely on analogies, because numbers alone fail to convey meaning. They'll tell you that if the solar system were the size of a coin, Andromeda would be the size of a continent, or that if the Milky Way were shrunk to the size of a dinner plate, Andromeda would be another dinner plate sitting nearby, and the entire observable universe would be the size of the Earth itself, filled with countless plates. These comparisons are attempts to shrink the immensity into something the mind can hold. But no matter how you frame it, the underlying reality is the same. Galaxies are immense, and Andromeda in particular is immense enough that when you look at it, you're seeing something larger than language can easily describe. The first glimpse of this scale often changes the way people think about their place in the universe. Our daily concerns operate on human scales: meters, kilometers, years, decades. Even when we stretch our thinking to the scale of history, of civilizations rising and falling, we are still talking about thousands of years, maybe tens of thousands at most. Galaxies operate on scales of millions and billions of years, of distances measured in light years that number in the hundreds of thousands. To glimpse that immensity, even for a moment, is to recognize that human history is a thin line drawn across a canvas so vast that it hardly registers. And yet, within that line, here we are, noticing, reflecting, asking questions. It's worth pausing to consider how long it took humanity to even realize what a galaxy is. For centuries, people saw Andromeda as nothing more than a nebula, a fuzzy patch within our own Milky Way. It was only in the 1920s that Edwin Hubble proved it was a galaxy in its own right, far beyond our own. That discovery expanded the universe overnight. Suddenly, the immensity of scale was undeniable. The Milky Way was not the whole universe, it was just one among many. Andromeda was no longer a cloud within our home, it was a home of its own, a sprawling system with its own stars, its own planets, its own scale of immensity. The immensity of galaxies is not only physical, it is also temporal. Stars within Andromeda have been shining for billions of years. Generations of stars have lived and died, seeding new generations with heavy elements, shaping the galaxy's evolution. When you look at Andromeda, you are seeing a snapshot of that long story, frozen at one moment in its history. The scale is not just about distance, but about time. The galaxy's stars span ages older than Earth itself, and they will continue to shine long after our own sun has gone quiet. To glimpse that scale is to feel both small and connected. Small because our lives are brief, and our planet tiny compared to galaxies. Connected because despite that smallness, we are made of the same materials, the same stardust forged in stellar cores, scattered across space, gathered into new stars and planets. The immensity of galaxies is not something separate from us. It is something we are part of. Andromeda is immense, but its atoms are the same kinds of atoms that form our own world, our own bodies. When you look at Andromeda, what you're really seeing is an opening into that immensity, a first glimpse, faint though it may be, of the true scale of the universe, and that glimpse is enough to spark the questions that carry us forward. If this galaxy is so large, what about the others? If our own galaxy is only one among billions, what does that mean for our place in the cosmos? How do we measure ourselves against scale so vast? These are not questions with easy answers, but they are questions worth sitting with. So the immensity of galaxies, and of Andromeda in particular, begins here, with the realization that the faint patch of light you see in the night sky is not just a blur, but an entire universe of its own, stretching across hundreds of thousands of light years, filled with nearly 1 trillion stars and surrounded by a halo of dark matter we cannot see but can feel through its gravity. That is the first glimpse of scale. It is overwhelming, humbling, and strangely comforting all at once. If Andromeda is this immense, how does it compare to our own galaxy? What makes it similar? What makes it different? And what does that tell us about the nature of galaxies themselves? When we speak about Andromeda as an immense galaxy, it's tempting to imagine it floating alone in the dark, an isolated island of stars adrift in the cosmic ocean. But galaxies do not usually exist in solitude. They gather in families, bound together by gravity, forming clusters and groups that move in relation to one another. Andromeda, as vast as it is not a solitary traveller. It belongs to a community of galaxies known as the local group, and within that group it holds a position of prominence. The local group is, in cosmic terms, a relatively small association of galaxies. It contains more than 50 members, though only a few of them are large. The rest are smaller companions, dwarf galaxies that cluster around the bigger ones like satellites. At the heart of the local group are 2 spirals of comparable importance, our own Milky Way and the Andromeda Galaxy. Between them, they dominate the gravitational landscape, their masses shaping the motions of everything else in the group. There is also a third major player, the Triangulum Galaxy, which is smaller but still significant. Together, these 3 form the backbone of the local group, with Andromeda as the largest member. To appreciate Andromeda's place, it helps to picture the local group as a kind of neighbourhood. Imagine a town spread out across a valley. Most of the houses are small, cottages and cabins scattered here and there, but among them are a few mansions, vast and imposing, that draw attention immediately. Those mansions are Andromeda and the Milky Way. They are the gravitational giants, their size and mass setting the tone for the neighbourhood. The smaller houses, the dwarf galaxies, cluster close to them, circling like families living in the shadow of their larger neighbours. Some of these dwarfs orbit the Milky Way, like the small and large Magellanic clouds visible in the southern hemisphere. Others orbit Andromeda, like M32 and M110, 2 small elliptical galaxies that sit nearby, almost like companions walking alongside a much larger figure. When astronomers chart the local group, they see that Andromeda lies about 2.5 million light-years from us, on one side of the group, while the Milky Way sits on the other. Between them stretches a gulf of space, but their mutual pull is strong enough that they are slowly moving toward each other. The Triangulum Galaxy lies near Andromeda, perhaps even bound as a satellite of it. The rest of the local group's members scatter around, some closer to one giant, some closer to the other, all bound together by their collective gravity. The entire group spans about 10 million light-years across, which sounds enormous, but compared to the larger clusters of galaxies beyond, it is small, modest, a quiet suburb in the vast city of the cosmos. Andromeda's role in this group is not just as a member, but as the heaviest and most influential member. Its mass, including dark matter, outweighs that of the Milky Way by perhaps 30 to 50%. Though measurements continue to refine, that extra heft gives Andromeda a stronger gravitational reach, shaping the motions of its satellites and influencing the dynamics of the entire group. When astronomers simulate the motions of the local group, they see Andromeda and the Milky Way drawn inexorably toward one another, destined to collide in about 4 billion years. That future merger will transform the local group entirely, blending the two giants into a single, even larger galaxy. It can be helpful to pause and consider the smaller galaxies that make up the local group. Some of them are so faint and diffuse that they were only discovered in recent decades, visible only through deep surveys with powerful telescopes. These dwarfs are interesting in their own right. They often contain only a few million stars, a drop compared to the trillions in Andromeda. Some are irregular in shape, more like smudges of stars than structured spirals. Others are elliptical, smooth and featureless. Many of them orbit close to the giants, their stars tugged and stretched by the larger galaxy's gravity. These small companions remind us that galaxies come in all scales, and that the local group is not just defined by its giants, but also by the interplay of the small with the large. The place of Andromeda in this context is both central and revealing. Without it, the local group would be a quieter, smaller association, dominated only by the Milky Way. With Andromeda, the group gains a balance, a sense of two giants locked in a long dance. The tension between them shapes everything else. Their combined gravity determines how the smaller galaxies move. Their eventual collision will decide the future of the group. To understand Andromeda is not just to understand a galaxy on its own, but to understand how galaxies live together, how they form communities, how they influence one another across millions of light years. Astronomers often study the local group as a laboratory for galactic evolution. Because it is nearby, its members can be observed in detail. By comparing the structures of Andromeda, the Milky Way, Triangulum and the dwarfs, scientists can test theories about how galaxies form, how they grow by accreting smaller companions, how star formation varies in different environments. In many ways, Andromeda's place in the local group is not just geographical, but intellectual. It is a cornerstone for our understanding of galaxies as a whole. There is also something comforting in realizing that the universe is structured in groups like this. The local group is not special. All across the cosmos, galaxies cluster into groups and clusters, bound by gravity, woven into filaments that form the large-scale structure of the universe. We happen to live in this group, with Andromeda as our nearest major neighbour. That nearness makes it familiar, almost approachable despite its immensity. To know that we are part of a group, that our galaxy is not alone but connected, gives a sense of belonging on a cosmic scale. If you think back to seeing Andromeda with your eyes, faint and fragile in the night sky, and then imagine it as the largest galaxy in a group of more than 50, the perspective shifts again. That blur you see is not only immense in itself, but also central to a network of galaxies, each with its own stars and stories. Andromeda's place in the local group is not just about its size, it is about its role as anchor, as neighbour, as counterpart to our own galaxy. Together these roles define the shape of our cosmic neighbourhood, the corner of the universe we call home. When we think of our own galaxy, the Milky Way, it is easy to picture it as the standard by which all others should be measured. After all, it is the one we inhabit. It is the framework that has shaped our view of the night sky for as long as humans have existed. But when we place it beside Andromeda, our nearest large neighbour, the comparison becomes both fascinating and humbling. These two galaxies are similar in many ways, yet in the details they differ, and those differences help us understand not only what each galaxy is like, but also what galaxies in general can become. The Milky Way is a barred spiral galaxy, its structure defined by a central bulge with a bar-shaped distribution of stars and long spiral arms extending outward. Andromeda too is a spiral galaxy, but it appears to lack a central bar, at least not as prominently as ours. Its arms are broader, its central bulge more pronounced, giving it a slightly different character. Both galaxies are rich with stars, gas, and dust. Both have satellite galaxies circling them. Both are cradled in halos of dark matter that extend well beyond the visible disks. But in terms of size and mass, Andromeda seems to have the upper hand. Measurements suggest that Andromeda is larger in diameter, about 220,000 light-years across compared to the Milky Way's estimated 100,000 to 120,000 light-years. That means if you place the two galaxies side by side, Andromeda would appear almost twice as wide. Its disk is broader, its spiral arms reaching farther into space. In terms of star count, Andromeda again pulls ahead. Where the Milky Way is thought to contain around 400 billion stars, Andromeda may contain close to 1 trillion. That makes it more populous, more crowded with suns, each of which may host its own family of planets. When astronomers measure mass, things become trickier. Dark matter makes up the majority of a galaxy's mass, and measuring it is difficult. Estimates vary, but many studies indicate that Andromeda's total mass, including dark matter, is greater than that of the Milky Way, perhaps by a factor of 1.5. Other measurements suggest the two may be more evenly matched than once believed. This uncertainty is part of the challenge of studying galaxies. Their visible stars are only the surface. Their true heft lies in the invisible scaffolding of dark matter. Even so, Andromeda is widely considered to be the heavyweight of the local group, its gravitational influence stronger, its pull more commanding. Yet the Milky Way is not without its strengths. Our galaxy is not simply a smaller copy. Its structure is different, its history unique. The bar at its centre shapes the flow of stars and gas, guiding material into its core and influencing star formation. The Milky Way also has a rich collection of satellite galaxies, including the large and small Magellanic Clouds, which are visible in the southern hemisphere as distinct smudges of light. And though Andromeda has more stars, the Milky Way's star formation rate, the number of new stars being born, is believed to be higher, making it, in some respects, the more active of the two. Comparing the two galaxies also means looking at their central regions. At the heart of both lies a supermassive black hole. In the Milky Way, that black hole is known as Sagittarius A, with a mass of about 4 million suns. In Andromeda, the central black hole is far larger, estimated at around 100 million suns. This immense difference gives Andromeda a more dominant gravitational anchor, one that shapes the motions of stars in its inner bulge and adds to its overall sense of scale. Yet despite its size, Andromeda's core is less active in terms of energy output than some black holes in other galaxies, suggesting it is not currently consuming matter at a high rate. The shapes of their spiral arms also differ. The Milky Way's arms are somewhat loosely wound, giving our galaxy a relatively open structure. Andromeda's arms are broader and contain more dust lanes, making them more dramatic in photographs and observations. These structural differences may be the result of past interactions. Both galaxies have histories of merging with smaller companions. The Milky Way shows evidence of having absorbed several dwarf galaxies in its past. Andromeda too bears scars of such mergers, its outer halo filled with streams of stars that once belonged to smaller galaxies torn apart by its gravity. These past events influence not only the appearance of each galaxy, but also their future trajectories. When comparing Andromeda and the Milky Way, it is tempting to frame them as rivals, as though one must be greater than the other. But in reality, they are partners in a cosmic relationship. Their masses pull on one another. Their satellites orbit in response to their combined gravity. Their future is entwined in a collision that will merge them into a single galaxy. So while Andromeda may be larger, and the Milky Way perhaps more active in star formation, their true significance lies in their relationship, in the way their similarities and differences are drawing them together. For us, the comparison is more than academic. It shapes how we imagine our own place in the universe. If Andromeda is larger, it reminds us that our galaxy is not the pinnacle of cosmic architecture, but one of many variations, If Andromeda's black hole is bigger, it challenges us to think about the range of possibilities galaxies can contain. If the Milky Way forms stars more quickly, it shows us that size is not everything, that vitality also matters. Each difference adds a piece to our picture of what galaxies can be. Another point of comparison is visibility. We see the Milky Way as a band across the night sky, its stars thickened by our position within its disk. Andromeda, by contrast, we see from the outside tilted at an angle that allows us to glimpse its structure as a whole. This difference in perspective is profound. Living inside the Milky Way, we cannot easily see its shape. We infer it from the motions of stars, from radio surveys of hydrogen gas, from mapping the positions of objects. Andromeda, though farther away, is visible as a coherent whole. By studying it, we learn not only about Andromeda itself, but also about what our own galaxy might look like to an observer elsewhere. In terms of environment, both galaxies sit in the same local group, surrounded by dwarf companions, influenced by one another's gravity. But their satellites differ. Andromeda's satellites include M32 and M110, both elliptical galaxies, as well as a host of faint dwarfs discovered in recent years. The Milky Way's satellites include the Magellanic Clouds and dozens of smaller dwarfs, some of which are barely visible. By comparing these satellite systems, astronomers learn about how galaxies gather and retain companions, how they interact with them, and how those interactions influence their growth. One of the most striking aspects of comparing the Milky Way and Andromeda is realizing how much we still do not know. Precise measurements of mass, structure, and history remain uncertain. Observations continue to refine our picture, but many details remain elusive. This uncertainty is not a flaw, but a feature of science. It reminds us that galaxies are not static objects to be catalogued once and for all. They are dynamic, evolving systems, and our understanding of them evolves as well. So when you place the Milky Way and Andromeda side by side in thought, what you see is not simply two galaxies of similar type. You see two variations on a theme, two expressions of galactic structure, each with its own strengths, its own history, its own role in the local group. And while one may be larger and the other more active, what matters most is that together they define our cosmic neighbourhood. To compare them is not to set them against each other, but to recognise the range of what galaxies can be, and to appreciate the fact that we have two such examples so close at hand. When you look up at the night sky and see that faint blur of Andromeda, it might seem impossible to imagine how scientists could ever measure something so distant, so vast, and so diffuse. How can we know how far away it is? How can we know how many stars it contains, or how much mass is hidden within it? These are questions that seem to stretch beyond what human senses are capable of, and yet astronomers have found ways. They have built methods step by step to measure the unmeasurable, to take something that seems unreachable and bring it into focus with numbers, distances, and comparisons. The starting point for much of this work is light itself. Light is the one messenger that crosses the gulf between galaxies and our eyes. Every photon that arrives carries information about the star it came from, about the gas it passed through, about the speed and distance of its source. By carefully studying that light, astronomers have built an entire science of measurement. It begins with brightness. When you see a star or a galaxy glowing in the sky, its brightness is a combination of two things: how luminous it really is and how far away it is. The farther it is, the fainter it appears. This relationship, though simple in principle, becomes a tool. If you can identify objects of known brightness, then their apparent faintness tells you their distance. These objects are sometimes called standard candles. One of the most important types is a class of stars known as Cepheid variables. These stars pulse in brightness over regular intervals, and the period of their pulsing is directly related to their intrinsic brightness. By measuring how long it takes for them to brighten and dim, astronomers can know how luminous they truly are. Then, by comparing that true brightness to how faint they appear from Earth, the distance can be calculated. This was the method used by Edwin Hubble in the 1920s to prove that Andromeda was not a nearby nebula, but a galaxy far beyond the Milky Way. He identified Cepheid variable stars within Andromeda, measured their periods, and from that determined its distance. That single measurement changed our understanding of the universe forever. Since then, other methods have been added. Supernovae, the explosions of massive stars, can also act as standard candles, especially a type known as type Ie supernovae. These explosions occur with consistent brightness, making them useful for gauging distances even greater than Cepheids can reach. In Andromeda, astronomers have observed such events, and by measuring them, they refine our estimates of its distance and scale. Another tool is redshift, the stretching of light as objects move away from us due to the expansion of the universe. For Andromeda, interestingly, the situation is reversed. Its light is slightly blue-shifted, meaning it is moving toward us rather than away. By measuring this shift, astronomers can determine its velocity relative to us, about 110 kilometers per second in our direction. This measurement not only tells us about Andromeda's motion, but also about the eventual collision between our galaxies in billions of years. Size is measured through a combination of angular extent and distance. From Earth, Andromeda spans a certain angle in the sky, several degrees if its faint arms were visible to the naked eye. By knowing its distance, that angle can be converted into a physical size. The larger the distance, the larger the galaxy must be to appear that wide. Through this method, astronomers estimate its diameter to be around 220,000 light-years. It's a deceptively simple calculation, but it depends critically on having accurate distance measurements, which is why the discovery of Cepheid variables was so crucial. Mass, on the other hand, is not something we can see directly. Instead, astronomers infer it from motion. The stars in a galaxy orbit around its centre. The speed of those orbits depends on the amount of mass pulling inward through gravity. By measuring the velocities of stars and gas in Andromeda, astronomers can calculate how much mass must be present to keep them moving as they do. What they find is that the visible stars and gas account for only a fraction of the mass. The rest must be invisible. This is where dark matter enters the story. The rotation curves of galaxies like Andromeda reveal that their outer stars orbit far faster than they should if only visible matter were present. The conclusion is that a vast halo of unseen mass surrounds the galaxy, outweighing the visible stars many times over. The precision of these measurements has improved with technology. Telescopes on the ground and in space allow astronomers to resolve individual stars in Andromeda, to track their motions, to detect faint variations in brightness. Instruments like the Hubble Space Telescope have given us not just clearer images but more accurate data. With every improvement, our picture of Andromeda's size, mass, and structure becomes sharper, and yet, uncertainty remains. Measuring galaxies is always an exercise in estimation, in models tested against evidence. Andromeda may be larger or smaller than current numbers suggest. Its mass may be heavier or lighter, depending on how dark matter behaves. The act of measurement is ongoing, never final. Beyond direct measurements, astronomers also use comparisons. By studying other galaxies at different distances, they can refine their understanding of how spiral galaxies behave. By looking at nearby dwarf galaxies orbiting Andromeda, they can infer the reach of its gravity. Each piece adds to the puzzle, building a more complete picture of Andromeda's true scale. It is remarkable, really, how much we know given how far away it is. To the unaided eye, Andromeda is nothing more than a blur. Yet through careful use of light, of motion, of mathematics, we have turned that blur into a measured, quantified object. We know its distance, we know its size, we have estimates of its mass. We can even project its future motion and predict its eventual collision with the Milky Way. All of this is possible because light carries information, and because human curiosity has built methods to decode that information. There is also something deeply human in the way these measurements are made. Astronomers did not simply wake up one day with the ability to weigh galaxies. They built it step by step, through centuries of effort, each generation adding one more tool. Ancient observers noticed the blur. Medieval astronomers catalogued it. Early modern scientists debated its nature. Then, with Cepheid variables, distances became measurable. With spectroscopy, motions could be tracked. With modern telescopes, individual stars could be resolved. Each advance was incremental, but together they transformed Andromeda from a mystery into a measurable object. And still, the sense of wonder remains. To say Andromeda is 2.5 million light-years away is to state a fact. To grasp what that means is another matter. To say it contains 1 trillion stars is to state a number. To imagine 1 trillion suns is another matter entirely. The methods of measurement give us numbers, but the human response to those numbers is still awe. The science does not diminish the mystery. If anything, it deepens it. Because now we know not only that Andromeda is vast, but just how vast. So when you look up at that faint blur, remember that it has been measured. Its distance has been gauged through variable stars. Its motion has been tracked through blue-shifted light. Its size has been calculated from its angular spread. Its mass has been inferred from the speeds of its stars. What seems unmeasurable has been made measurable, at least in part. And each of those measurements brings us closer to answering the question we began with. How big is Andromeda really? When we imagine a galaxy, the image that often comes to mind is that of a spiral. Elegant arms sweeping outward, stars and dust arranged in arcs that look almost like a painting. This is not just an artistic impression. Spiral structure is one of the defining features of galaxies like Andromeda, and its arms are not only beautiful but deeply informative. They tell us about how stars are born, how matter moves, and how the galaxy maintains its balance across such vast scales. To talk about the shape of Andromeda is to move from the abstraction of size into the detail of structure, into the patterns that give this immense system its character. When you look at photographs of Andromeda taken through telescopes, the first thing you notice is its bright central bulge. This is the densely packed core of the galaxy, a sphere of older stars shining with a yellowish light. From this bulge, arms spiral outward, broad and sweeping. They are not thin lines, but thick regions filled with stars, dust and gas. In colour images, the arms appear mottled, with patches of blue where young hot stars burn, and streaks of dark where dust clouds absorb the light. These contrasts give the arms texture, a kind of roughness that reflects the ongoing processes inside them. The arms themselves are not solid structures. They are patterns, regions where density is higher, where stars and gas are more concentrated. Think of them less as permanent walls of stars and more as traffic jams on a cosmic highway. Stars move through the arms, entering, lingering and leaving, while the pattern of the arm persists. This idea, known as density wave theory, explains how spiral arms can exist for billions of years without winding up completely from the rotation of the galaxy. The arms are not made of the same stars forever. They are regions where stars bunch up, like waves moving through water. Within Andromeda's spiral arms, new stars are born. Clouds of gas collapse under gravity, igniting nuclear fusion, creating clusters of bright young stars that light up the surrounding regions. These young stars are often blue because they are hot and massive. They do not live long, only a few million years, but their brightness marks the arms clearly. Alongside them, regions of red and pink appear in images. Emission nebulae, where ultraviolet light from young stars excites hydrogen gas, making it glow. These glowing clouds are nurseries, places where galaxies refresh themselves with new generations of stars. The dust lanes that thread through Andromeda's arms are just as important. They may look like shadows, dark streaks obscuring the starlight, but they are actually reservoirs of raw material. Dust and gas in these regions are the seeds of future stars. Without them, the arms would be bright but static. With them, the arms are dynamic, constantly producing new stars, constantly evolving. To trace the shape of Andromeda's arms is to trace its ongoing life, its cycles of birth and death played out on a galactic stage. The symmetry of Andromeda's spiral is striking but not perfect. Its arms are not identical, not evenly matched. One appears broader, another thinner, with knots and irregularities scattered throughout. These asymmetries may be the result of interactions. Andromeda has smaller companion galaxies, and as they pass near or even through its disk, their gravity can tug on the arms, pulling them out of shape, stirring new waves of density. Over time, these interactions leave their marks, giving the spiral arms a history written in their distortions. If we could see Andromeda as it truly appears in the sky, not limited by the faintness of our eyes, its arms would stretch across several degrees. It would be larger than the moon, larger than the sun, a sprawling structure hanging visibly overhead. Imagine standing outside at night and seeing spiral arms arcing across the sky, their mottled light visible without aid. That is the true shape of Andromeda, hidden only by the limits of human vision. Telescopes reveal it to us, but the reality is always there, even when we cannot see it directly. The shape of Andromeda also extends beyond its visible arms. Surrounding the galaxy is a vast halo of stars, faint and diffuse, stretching far outward. Within this halo are streams of stars, remnants of smaller galaxies that Andromeda has consumed. These streams arc around the main disk, tracing past interactions. They show that the galaxy's shape is not static. It is constantly evolving, constantly absorbing, constantly reshaping itself through encounters. The arms are the most visible part, but the true structure of Andromeda includes all these layers, from the bright bulge to the faint outskirts. When astronomers study the arms, they do not just look at their beauty. They measure the rotation of stars within them, the distribution of gas, the rates of star formation. They build models of how density waves move through the disk, how spiral structure can persist over billions of years. And by comparing Andromeda's arms to those of other galaxies, they test theories of galactic dynamics. The arms are not decoration. They are a record of physics in action, written on a scale so vast that we can only comprehend it through patient study. For us, the arms are also a reminder of the patterns that recur in nature. Spirals are everywhere, from seashells to hurricanes to galaxies. The mathematics of spirals reflects balance, growth, and motion. In Andromeda, the spiral arms are that pattern writ large, repeated on a scale of hundreds of thousands of light years. To notice them is to see continuity between the small and the immense, between the patterns of life on Earth and the structures of galaxies in space. If you imagine drifting closer to Andromeda, flying toward it across the void, the arms would grow larger, their structure more apparent. You would see clusters of stars gathered in knots, clouds of gas glowing pink, lanes of dust weaving through. You would see regions of calm and regions of turbulence. You would see star clusters forming, some so massive they shine brighter than any cluster in the Milky Way. You would see supernova remnants, shells of gas thrown outward by dying stars. The arms are not uniform. They are varied, textured, alive with activity. One of the remarkable things about Andromeda's arms is how they help bridge our understanding of our own galaxy. From inside the Milky Way, we cannot see its spiral structure directly. We infer it from the distribution of stars and gas, but we do not have the outside view. Andromeda gives us a model. By studying its arms, we learn what spiral arms look like from the outside, and then we apply that knowledge to interpret what we see from within. Andromeda is not just a neighbour, it is a mirror, showing us what we cannot see about our own home. The arms also remind us of the scale of time. A spiral galaxy does not rotate like a solid disk. Its stars move at different speeds depending on their distance from the centre. Over billions of years, the arms maintain their pattern, not because the same stars stay in place, but because the density wave moves through, shaping the positions of stars and gas. This means the spiral we see today is not the same spiral that existed 1 billion years ago, nor the same spiral that will exist 1 billion years from now. The pattern persists, but the details change. The arms are both permanent and impermanent, enduring yet constantly renewed. To appreciate the shape of Andromeda is to recognize that structure itself is part of the story of size. The arms define the galaxy's appearance, but they also define its scale. When we say Andromeda is 220,000 light-years across, what we're really saying is that its arms reach that far, that its spiral pattern extends across that distance. Without the arms, the galaxy would be only its bulge, much smaller, less immense. The arms are what give Andromeda its true size, and so, in tracing their arcs, we move closer to answering our question. How big is Andromeda really? It is as big as its arms, as broad as the waves of stars and gas that sweep outward, as vast as the dust lanes and nurseries that form within them. The spiral is not just a shape, it is a measure of immensity, drawn across space in arcs that stretch farther than our imaginations are ready to travel. What are the stars that populate them? How many are there? How do we begin to count the uncountable, to take the spiral shape and turn it into a number of suns? When we talk about the immensity of Andromeda, one of the simplest yet most staggering measures is the number of stars it contains. To stand beneath the night sky and see that faint blur, then to be told that within it are hundreds of billions of stars, each one a sun in its own right, is almost too much to take in at once. Numbers that large slip quickly out of the grasp of daily experience. We can picture a few, we can picture 100, perhaps 1,000, but billions upon billions become abstractions. And yet astronomers have tried to count, to estimate, to turn the blur into a census of stars. The first step in this process is to understand that no one has ever literally counted the stars in Andromeda. The galaxy is too far, and the stars too numerous. Instead, astronomers estimate by measuring the light. Every star contributes a tiny portion of light, and when combined, the galaxy shines as a whole. By measuring the total brightness and comparing it to models of stellar populations, astronomers can estimate how many stars must be present to produce that glow. It is a method that relies on averages, on assumptions about the distribution of star types, but it gives us a number to hold on to. Those estimates suggest that Andromeda contains close to 1 trillion stars. A trillion is 1,000 billion. It is more than double the estimated number in the Milky Way. To give some sense of scale, imagine you were to count one star every second without stopping. To reach 1 trillion would take you more than 30,000 years, and by the time you finished your list would already be out of date, because stars would have been born and died while you counted. The act of numbering them is symbolic. It is not about precision, but about appreciating magnitude. The stars of Andromeda are not all the same. They range from massive blue giants that burn hot and die young, to cool red dwarfs that linger for tens or even hundreds of billions of years. The vast majority are red dwarfs, small and dim, invisible to the naked eye even from nearby. These are the quiet majority, the countless faint suns that form the backbone of the galaxy's population. A smaller fraction are stars like our own sun, yellow and steady, burning for billions of years, and then, scattered throughout, are the giants, the bright, massive stars that light up the spiral arms. Each type plays a role in shaping the galaxy's character. Astronomers study these populations by examining the spectrum of Andromeda's light. When light is spread into its component colours, it reveals signatures of the types of stars within it. Certain absorption lines correspond to certain elements, which in turn correspond to the temperatures and types of stars producing the light. By comparing this data to models, astronomers can estimate the distribution of star types. From there, they can infer not only the number of stars but also the total mass of the galaxy. The process also reveals something about the history of star formation in Andromeda. The galaxy has not produced stars at a constant rate. There were periods of intense activity, when stars formed rapidly, and quieter periods, when formation slowed. These cycles are written into the populations we see today. Young blue stars mark recent formation. Older, redder stars mark the remnants of earlier generations. The mixture tells the story of billions of years, of a galaxy constantly renewing itself through the birth and death of stars. One of the most humbling aspects of this star count is the recognition that each star is potentially a system of its own. Many stars have planets. Many planets have moons. Each system is its own miniature cosmos. To say Andromeda contains 1 trillion stars is to say it contains perhaps trillions of worlds. Most of those worlds will be barren, but even a small fraction that are not would represent an unimaginable abundance of possibilities. The numbers quickly become so large that they defy comprehension, and yet they are real, grounded in the light we can measure. If you try to visualize the stars of Andromeda, it may help to imagine the night sky here on Earth. On the darkest nights, free of light pollution, you can see perhaps a few thousand stars with your naked eye. Through a small telescope, tens of thousands become visible. The Milky Way, as seen from within, appears as a river of countless stars, too many to distinguish individually. Now take that sense of abundance and multiply it by hundreds of billions. That is Andromeda. Every point of light in its disk, every faint shimmer in its halo, is another sun. The scale is such that even our richest night skies are a tiny fragment by comparison. The attempt to count stars is also an attempt to connect numbers to reality. 1 trillion is not just an abstract quantity. It is 1 trillion suns shining, each with its own path through the galaxy, each contributing to the collective glow. They orbit the galactic centre in vast streams, some in tight circles near the core, others in wide arcs far from the disk. Together they form the gravitational balance that holds Andromeda together. Without their combined mass, the spiral arms would not persist, the rotation would not be stable. The stars are not just lights, they are the fabric of the galaxy. Andromeda's population of stars also includes relics of smaller galaxies it has absorbed. Streams of stars in its halo are the remnants of such mergers, strands pulled apart by gravity and stretched across space. These stars add to the count, blending into Andromeda's structure but carrying histories of their own. The galaxy is not just a static collection of stars but an evolving system, growing over time by incorporating others. Each new addition increases the number, increases the mass, increases the immensity. To put the star count in perspective, consider again that the Milky Way contains perhaps 400 billion stars. That is itself an overwhelming number. Yet Andromeda contains more than twice that. It is the heavyweight of the local group, not only in size but in population. When we compare the two, we see that our galaxy, for all its richness, is smaller, less crowded. Andromeda's greater number of stars may also influence its future collision with the Milky Way. The resulting galaxy will be a blend of both, a system containing more than 1.5 trillion stars, reshaped into a new form. Counting stars may seem like an academic exercise, but it has practical implications. The number of stars determines the total light, the total mass, the total gravity. It influences how the galaxy interacts with its neighbours, how it evolves over time. It also sets the stage for the search for exoplanets, and, by extension, the search for life. If our galaxy alone offers billions of possible worlds, then Andromeda, with its greater number of stars, offers even more. The act of counting is not just about size, it is about imagining possibilities, about recognizing that within one galaxy lies more than we could ever explore. When you look up and see that faint blur, it is easy to forget all of this. It seems so small, so modest. But hidden within that blur are 1 trillion stars, each one a sun, each one contributing to the glow that reaches your eyes. To know that is to change the way you see it. It is no longer just a smudge. It is a city of stars, a metropolis on a scale beyond comprehension, shining across millions of light years to be glimpsed in a single glance. When we think of galaxies, the first image that comes to mind is usually of stars, bright points of light, countless in number, arranged into spirals or spheres. But stars are only part of the picture. Between them lies something less obvious but just as essential: the dust and gas that fill the galaxy, the material that makes galaxies breathe. Without this interstellar medium, galaxies would be static collections of suns, their fates sealed by the slow burn of fusion until nothing remained. With dust and gas, galaxies are alive, capable of renewing themselves, of giving birth to new generations of stars, of changing shape and structure over time. In Andromeda, as in other spiral galaxies, this medium is concentrated in the disk, woven into the spiral arms. Dust and gas may sound insubstantial, but they make up a significant portion of the galaxy's visible mass. Clouds of hydrogen stretch across hundreds of light years, cold and dark until something disturbs them. When they collapse under gravity, stars form. Dust grains, tiny particles of heavier elements scatter light, reddening and dimming the stars behind them. Together, dust and gas create the mottled appearance of Andromeda's arms, with bright clusters of young stars interspersed with dark lanes that seem to cut across the light. To the eye, dust may look like an absence, a shadow, but in reality, it is potential. It is the raw material of stars and planets. Within dense clouds of dust and gas, temperatures can be low enough for molecules to form, hydrogen combining into molecular clouds that become stellar nurseries. In Andromeda, vast regions of these nurseries exist, glowing faintly in infrared light. Through visible telescopes they appear as dark patches, but with instruments that can see beyond visible light, they reveal themselves as glowing structured clouds. These are the lungs of the galaxy, the places where it breathes out new stars. Gas also plays a role in the dynamics of Andromeda. The motion of hydrogen clouds has been mapped in detail with radio telescopes, which can detect the specific emission line of neutral hydrogen at 21 centimeters. By tracing this emission, astronomers can see how gas moves within the galaxy, how it orbits, how it clumps, how it feeds star formation. These maps reveal structures beyond what is visible in starlight, showing arms of gas that extend farther than the stars themselves. They also provide crucial evidence for dark matter, because the speeds at which gas clouds orbit cannot be explained by visible mass alone. The dust, too, carries information. By absorbing and scattering starlight, it alters the colours we see, a process called extinction. By measuring this effect, astronomers can estimate how much dust is present, where it lies, and how it shapes our view of the galaxy. Infrared telescopes like Spitzer and Herschel have shown that Andromeda contains vast reservoirs of dust, arranged in rings and arcs that trace its structure. These patterns may be the result of interactions with smaller galaxies, gravitational nudges that compressed gas and dust into new arrangements. Without dust and gas, galaxies would eventually go dark. Stars would age and die, leaving behind remnants, but no new stars would take their place. It is the continuous cycle of gas collapsing into stars, stars fusing elements and exploding, scattering enriched material back into space, and new stars forming again that keeps galaxies dynamic. In Andromeda, this cycle has been ongoing for billions of years. The heavy elements found in its dust grains were forged in earlier generations of stars, spread by supernovae, gathered again into clouds. Each cycle enriches the next, seeding planets with the materials needed for complex chemistry, perhaps even for life. When we describe Andromeda as immense, we often focus on its stars, its arms, its diameter. But its immensity is also in this cycle, in the ongoing process of breathing through dust and gas. The galaxy is not a finished object. It is a living system, sustained by the interplay between light and shadow, between stars that shine and clouds that conceal. This dynamic is what makes spiral galaxies like Andromeda so visually striking. The contrast of bright clusters and dark lanes is not just aesthetic, it is evidence of the processes that sustain the galaxy's existence. It is worth remembering that dust and gas also shape our own view of the universe from Earth. The Milky Way's disk is filled with dust that blocks our sightlines, making certain regions opaque in visible light. Without dust, we could see farther, but we would also lose the material needed for new stars. The obscuring is a trade-off, one that astronomers have learned to work around by observing in other wavelengths. In Andromeda, dust both hides and reveals, depending on how we look. It hides stars behind it, but it reveals structure in infrared, outlines of processes invisible otherwise. The scale of these clouds is difficult to grasp. Some span dozens or even hundreds of light years, containing enough material to form thousands of stars. Within them, pockets collapse, forming clusters. The rest may linger for millions of years before dispersing. Each cloud is part of a larger pattern, moving through the spiral arms, influenced by density waves, by the gravity of nearby stars, by the shocks of supernova explosions. It is a constantly shifting environment, full of turbulence and change, yet ordered enough to produce new generations in a steady rhythm. In Andromeda, the distribution of dust and gas shows rings that are unusual. Unlike the smooth spirals of many galaxies, Andromeda's dust is arranged in concentric features, as though waves have rippled outward. Astronomers believe this may be the result of a past collision with a smaller galaxy, which disturbed Andromeda's disk and set off waves of star formation. These rings are evidence that galaxies carry memories of their past interactions in their very structure. To study Andromeda's dust and gas is to read its history, to see not only what it is now, but what has shaped it over time. This interplay between stars, dust, and gas also explains why galaxies can sustain themselves for billions of years. Stars return material to the interstellar medium through stellar winds and supernovae. That material, enriched with heavier elements, becomes part of the dust and gas clouds. New stars form from those clouds, inheriting the enriched material. Planets form around those stars, incorporating the dust. The cycle continues. In this way, galaxies are not static, but evolving ecosystems, with dust and gas as the medium that carries their renewal. To think of Andromeda as breathing is not just a metaphor. It captures the rhythm of inflows and outflows, of cycles of star birth and death. The galaxy inhales gas, gathers it into dense clouds, and exhales starlight and enriched material. This rhythm is not as quick as a human breath. It unfolds over millions of years. But it is a rhythm nonetheless, a pulse of creation that sustains the galaxy. And if we step back from the detail, we see that this breath defines Andromeda's character. Its bright arms are outlined not just by stars but by dust and gas. Its structure is sculpted by where material has gathered, where it has collapsed, where it has been blown away. Its future will be determined in part by how much gas remains, by how much potential for new stars is left. One day, far in the future, Andromeda may exhaust its reserves, becoming a quieter galaxy where few new stars form. But for now, it is still breathing, still alive with cycles of birth and renewal. When we ask how big Andromeda really is, dust and gas must be part of the answer. They extend beyond the visible stars, forming halos and structures we can only see in certain wavelengths. They add mass, they shape the light, they fuel the future. The immensity of the galaxy is not just in its size or its stars, but in the medium that fills it, the hidden substance that makes galaxies into living systems rather than static collections of suns. At the very centre of Andromeda, past the spiral arms, past the rings of dust, past the swarms of stars orbiting in dense clusters, lies something invisible. It cannot be seen directly, because its gravity is so intense that not even light can escape it. And yet, its presence is undeniable, revealed by the way everything around it moves. This is the supermassive black hole at the heart of Andromeda, an object millions of times the mass of our Sun, a gravitational anchor around which the entire inner galaxy turns. When people hear the phrase black hole, they often picture it as a kind of cosmic vacuum, sucking in everything nearby. But a black hole, even one as immense as this, is not simply an emptiness. It is a region where matter has collapsed to such density that the laws of physics as we know them bend. At its core lies a singularity, a point where density becomes infinite, surrounded by an event horizon, the boundary beyond which nothing can return. Around that horizon, matter swirls, heated by friction and gravity into extreme states. The black hole itself is dark, but the space around it can glow with incredible brightness as gas and dust spiral inward. In Andromeda, the central black hole is estimated to have a mass of about 100 million suns. Compare that to the black hole in our own galaxy, Sagittarius A, which weighs about 4 million suns. The difference is staggering. Andromeda's black hole is a giant even among giants, one of the heaviest known in galaxies of its type. That immense mass exerts a gravitational influence far beyond its event horizon, shaping the orbits of stars in the bulge, dictating the rhythm of the galaxy's heart. Astronomers detect its presence not by seeing it directly, but by observing those orbits. Stars near the centre of Andromeda move at extraordinary speeds, whipping around in paths that cannot be explained by visible matter alone. By mapping their motions, scientists infer the mass that must be hidden there. The result points consistently to a supermassive black hole, invisible but undeniable. Some of the fastest moving stars in Andromeda trace their paths close to this core, and by studying them, astronomers refine their estimates of the black hole's mass. Despite its size, the black hole in Andromeda is relatively quiet by cosmic standards. In some galaxies, central black holes are active, consuming material at high rates, producing jets of energy that shine across millions of light years. These are called quasars, or active galactic nuclei. Andromeda's black hole, by contrast, is not currently feeding in large amounts. It lies relatively dormant, consuming little, emitting faint radiation compared to the most active galaxies. This quietness is fortunate for us, because a more active black hole would bathe the local group in high-energy radiation. Instead, Andromeda's black hole is content to sit in silence, an immense weight holding the galaxy's core together. The size of this black hole raises questions about how it grew. Did it begin as a smaller black hole formed from the collapse of an early massive star and then accrete material over billions of years? Or did it grow quickly in the early universe, perhaps through the merger of multiple smaller black holes? Its mass suggests a long history of growth, likely involving both accretion and mergers. And because Andromeda itself has absorbed smaller galaxies, their central black holes may have merged into its own, contributing to its size. Each collision would have been a violent event, releasing immense energy, reshaping the galaxy's core. What makes the idea of a central black hole so striking is not only its mass, but its role. It is not just an object within the galaxy, it is part of the galaxy's identity. The motions of stars in the bulge, the flow of gas, even the shape of the inner structure are all influenced by this hidden anchor. Without it, the galaxy would not move as it does. In that sense, the black hole is as much a part of Andromeda's immensity as its spiral arms or its halo of stars. It is the unseen centre, the weight around which everything turns. To imagine the environment near this black hole is to step into extremes. Gravity there is intense enough to bend the paths of light to stretch time itself. Gas falling inward is heated to millions of degrees, glowing in X-rays. Magnetic fields twist and snap. Space itself curves. If you could somehow orbit close enough without crossing the event horizon, time for you would slow relative to the rest of the universe. From your perspective, the galaxy would seem to race ahead while you lingered. This is not science fiction, but a consequence of general relativity. the theory that describes how gravity bends space and time. Though invisible to our eyes, Andromeda's black hole can be detected in high-energy light. Observations with X-ray telescopes have revealed faint emissions from gas near the event horizon. These signals are weak compared to active galaxies, but they confirm that the black hole is there, influencing matter in its immediate surroundings. Future instruments, perhaps even ones like the Event Horizon Telescope that imaged the black hole in M87, may one day capture a direct image of Andromeda's black hole. For now, we know it primarily through its effects. The presence of such a massive black hole also shapes the galaxy's future. When Andromeda and the Milky Way collide billions of years from now, their central black holes will eventually spiral toward one another and merge. The resulting black hole will be even larger, a giant weighing hundreds of millions of suns. That merger will release gravitational waves, ripples in space-time that spread across the cosmos. Even though it will happen long after humanity is gone, the prediction is clear. The central black holes are not just silent anchors. They are participants in cosmic events that unfold over timescales beyond our comprehension. It is humbling to think that at the centre of the faint blur you can see with your eyes lies something so extreme. A black hole 100 million times the mass of the Sun, hidden in plain sight, shaping the orbits of billions of stars. It is a reminder that galaxies are not only collections of stars but also hosts of mysteries, objects that stretch our understanding of physics itself. And yet, the black hole is not alone in Andromeda's core. Surrounding it are dense clusters of stars moving at breakneck speeds, interacting through gravity in complex ways. Some of those stars may eventually be consumed by the black hole, falling past the event horizon and disappearing forever. Others will slingshot outward, flung into the galaxy at extreme velocities. The core is a place of constant activity, even if the black hole itself is quiet on a cosmic scale. To understand Andromeda fully, we must include this hidden heart. It is part of the galaxy's size, part of its weight, part of its story. Without it, the motions of the bulge would make no sense. With it, the galaxy becomes coherent, structured around an invisible anchor. The immensity of Andromeda is not only in its arms and stars, but in this single point, this singularity where physics bends and scale becomes almost meaningless. When we picture Andromeda, we often imagine it alone, a grand spiral galaxy suspended in the dark, its arms stretched wide, its centre glowing. But no galaxy of that size is ever truly alone. Just as the Milky Way has its own companions, like the large and small Magellanic Clouds, Andromeda too is surrounded by a retinue of smaller galaxies. These satellites are faint, far less imposing than their giant neighbour, but they are bound to it by gravity, orbiting it across millions of years. Together they make up a system, a family of galaxies with Andromeda at the centre. To understand how large Andromeda really is, we must consider not only its disk and halo, but also the company it keeps. The two most prominent companions are M32 and M110. Both are elliptical galaxies, small compared to Andromeda, but significant in their own right. M32 is compact, dense, with stars packed tightly together, making it appear unusually bright for its size. It may once have been larger, stripped down by Andromeda's gravity, leaving behind only its concentrated core. M110 is more diffuse, an elliptical with a fainter glow, trailing streams of stars that suggest it too has been shaped by its interactions with Andromeda. These two companions orbit close to the main galaxy, visible even in small telescopes as faint patches near the spiral's disk. Beyond these, Andromeda hosts dozens of dwarf galaxies. Many are so faint that they were only discovered in the last few decades, detected by careful surveys that revealed subtle overdensities of stars against the background. Some of these dwarfs are irregular in shape, looking more like smudges of scattered stars than structured galaxies. Others are spheroidal, smooth and faint, little more than shadows in the dark. Each one contains perhaps millions or tens of millions of stars. tiny compared to Andromeda's trillion, but still enormous compared to anything we can experience directly. The relationship between Andromeda and its satellites is not static. Gravity is constantly at work, pulling, stretching, distorting. Some of the smaller galaxies are being tidally disrupted, their stars drawn into long streams that wrap around Andromeda. These streams are visible in deep images, delicate arcs of stars that trace the paths of past encounters. They are evidence that Andromeda has grown over time by consuming its companions, tearing them apart and absorbing their stars into its own halo. This process is ongoing. Even now, some of Andromeda's satellites are being digested, their structures stretched and dissolved into the larger galaxy. This behavior is not unique to Andromeda. The Milky Way does the same, currently in the process of consuming the Sagittarius dwarf galaxy, which is being pulled into streams that wrap around our galaxy. But because Andromeda is larger, its influence is stronger, its reach longer. The number of satellites it has absorbed over billions of years may be far greater, and the evidence of those interactions is written in its halo. The streams and shells of stars surrounding Andromeda are the fossil record of its galactic meals. Studying these satellites is important because they tell us about the environment in which Andromeda exists. The number of dwarfs, their distribution, their histories, all of these inform our understanding of dark matter. According to cosmological models, large galaxies should be surrounded by many smaller ones, each embedded in its own dark matter halo. The fact that Andromeda and the Milky Way each have dozens of known satellites supports this picture, though there are debates about whether there are fewer dwarfs than expected. Each discovery of a new faint satellite adds to the tally, helping to test our theories of how galaxies form and evolve. For us, the satellites also shift the picture of Andromeda's size. The galaxy is not only its disk of 220,000 light-years, it is the entire system of companions that orbit it, extending its reach across millions of light-years. To say Andromeda is immense is to include these satellites, to recognize that its influence stretches far beyond its visible spiral. Its gravitational domain encompasses not only its own stars but those of dozens of other galaxies, each one a piece of the system. There is also a story in the diversity of these satellites. Some are gas-rich, irregular galaxies where stars still form. Others are gas-poor, quiescent, filled only with old stars. The difference often depends on how close they are to Andromeda. Satellites that pass near the giant tend to lose their gas, stripped by gravitational tides and by the pressure of Andromeda's halo. Without gas, star formation ceases, and the galaxy becomes a faint shell of older stars. Those that remain farther away can retain their gas and continue forming stars. This interaction shows that Andromeda is not only a passive neighbour, it actively shapes the fate of its satellites, deciding which live on as active galaxies and which fade into quiet relics. Some of the faintest satellites of Andromeda are barely visible even to powerful telescopes. They are diffuse, stretched out with surface brightness so low that they blend into the background. Detecting them requires sensitive surveys that can pick out small clumps of stars moving together. The discovery of these ultra-faint dwarfs has expanded our understanding of how complex a galactic system can be. Andromeda's family is larger and more varied than we once thought, a reminder that galaxies are not solitary entities but communities. The satellites also play a role in Andromeda's own evolution. As they orbit, they deposit stars and dark matter into the larger halo. Their gravitational tugs may distort the spiral arms, creating asymmetries, rings, or warps in the disk. Over time, their interactions contribute to the overall structure of the galaxy. In this sense, Andromeda is not a finished object, but a work in progress, constantly reshaped by the company it keeps. If you imagine drifting outward from Andromeda, leaving behind its bright core and broad spiral arms, you would begin to encounter these satellites scattered around it. Some would appear as compact glows, others as faint smudges, others as nearly invisible groups of stars. Each one would have its own history, its own path, but all of them would be bound by Andromeda's gravity, part of its domain. The galaxy's true size is not just in its disk, but in this entire system, a sprawling arrangement of dozens of smaller companions. The presence of satellites also reminds us of scale. A dwarf galaxy with a few million stars would be immense if placed beside our solar system. It would dwarf every structure we know on Earth. Yet compared to Andromeda, it is tiny, almost negligible. The contrast between the giant and its companions is striking. Andromeda is the heavyweight, the dominant mass, while the satellites are whispers, fragments of light circling in its shadow. Still, without them, the picture would be incomplete. They are the supporting cast that reveals the scale of the main actor. To study Andromeda is to study this whole ensemble. The galaxy is not a single object, but a network, a system of interactions. Its satellites tell us how it grows, how it influences its surroundings, how it fits into the larger structure of the local group. They show us that even in the immensity of galaxies, relationships matter. Andromeda's size is not just a number of light years. It is the space it commands, the company it keeps, the gravitational family that revolves around it. Every time you look up at the sky, you're not seeing it as it is, but as it was. Light does not travel instantly. It takes time to cross the gulf of space, and so the stars and galaxies we see are always shifted into the past. With nearby objects, the delay is small. Light from the moon takes just over a second to reach us. Light from the sun takes about 8 minutes, but with Andromeda, the scale changes dramatically. Its light takes 2.5 million years to arrive. That faint blur in the sky is not Andromeda as it exists tonight, but Andromeda as it was long before humanity began. To think about this is to recognize that seeing is also time travel. When photons from Andromeda enter your eyes, they began their journey before our species existed, before cities, before writing, even before what we would recognize as civilization. They left their stars in a time when early humans were still shaping stone tools, when ice sheets spread across continents, when the Earth was in a very different chapter of its history. Every glance at Andromeda is a direct connection to that past. This delay is not unusual in astronomy. It is the rule. Every object we observe is a record of an earlier time. But with Andromeda, the delay is just the right scale to feel both immense and approachable. It is immense because 2.5 million years is far beyond human lifetimes, far beyond even the span of civilizations. It is approachable because it is still close enough that the galaxy appears visible to the naked eye. Most galaxies we can see through telescopes are tens or hundreds of millions of light years away. Their light older than humanity itself. Andromeda, by contrast, carries a message from a time that, while ancient, is still connected to the story of our own species. The light we see from Andromeda is a blend. It comes from billions of stars, each at a different stage of life, each shining with its own brightness and colour. Some of those stars have already burned out. Some have exploded as supernovae. Others may have changed in brightness. But their light continues on, carrying the record of what they were 2.5 million years ago. The galaxy we see is a fossil, a snapshot frozen in transit. To observe it is to read a chapter from the past, even as the present continues unseen beyond our reach. Astronomers use this property of light to study not only Andromeda but the universe itself. By looking farther away, they look deeper into time. The most distant galaxies we observe are seen as they were billions of years ago, not long after the universe began. In this way, the sky is a record, each distance corresponding to a different time. Andromeda is one of the nearer chapters, but even it carries us beyond human history into prehistory. To see it is to connect with a world long gone yet still present through the persistence of light. There is also a humbling recognition that the Andromeda we see tonight may be different from the Andromeda that exists tonight. Stars may have shifted, clusters may have evolved, supernovae may have flashed and faded. The galaxy continues its life while we see only its past. If we could suddenly switch to seeing it in real time, the differences would be subtle to the eye but profound in meaning. we would be catching up with millions of years of evolution. But as it is, we are always behind, always looking back. This is not a flaw of observation. It is the nature of the universe. The light that reaches us is not all the same. Some of it is visible, some infrared, some ultraviolet. Each wavelength tells a different story. Visible light reveals the stars, the shapes of the arms, the glow of the bulge. Infrared light penetrates dust, showing the cooler structures, the hidden nurseries of stars. Ultraviolet highlights the youngest, hottest stars, blazing with energy. X-rays reveal the violent processes near the black hole and in the remnants of supernovae. Each band of light arrives across time, carrying a different layer of the galaxy's history. Together they form a composite picture, a richer record than any single wavelength could provide. To the human eye, Andromeda's light is faint, almost ghostly. It takes effort to notice. But to a telescope, especially one with a camera capable of long exposures, that same light becomes vibrant. By collecting photons over minutes or hours, telescopes can accumulate what the human eye cannot. The result is an image where Andromeda's structure comes alive, where its spiral arms are detailed, where its dust lanes are sharp, where its stars are resolved into clusters. The light was always there, falling upon Earth in silence. The telescope simply gathers enough of it to reveal what our eyes alone cannot. It is striking to think that every photograph of Andromeda is built from photons that began their journey millions of years ago. Each pixel of those images is a record of ancient light. Each colour, each shape, is a message carried across space and time. The galaxy is both far away and intimately close, because its light is right here, falling into our instruments, into our eyes. We do not have to travel to it to know it. It comes to us unceasingly, a river of light that began long ago and will continue long after us. The concept of light across time also connects us to the idea of cosmic history. When we look at Andromeda, we are not just seeing a distant galaxy. We are seeing a stage in its life, a moment in its evolution. 2.5 million years may seem long to us, but for a galaxy it is brief, a blink. Andromeda existed long before that moment, and it will exist long after. The light we see is one frame in a film that stretches across billions of years. The immensity of its scale becomes not only spatial but temporal. It is easy to forget that the photons arriving now are not the first, and they will not be the last. Every night new waves of light arrive, each carrying its own slice of history. This flow is continuous, a steady rain of ancient signals. To lie under the stars and gaze at Andromeda is to immerse yourself in that flow, to let it wash over you, to feel, however briefly, that you are part of a story that extends far beyond human time. There is also something personal in this recognition. When you look at Andromeda, you're seeing light that no one else will see in quite the same way. The photons that enter your eyes are absorbed, their journey ending with you. Others will follow, but those particular ones are yours alone. They travelled for millions of years to reach you, and in that sense the connection is direct, individual. The galaxy is immense, but its light is intimate, shared one photon at a time. This intimacy does not diminish the immensity. If anything, it makes it more powerful. To know that something so vast can reach you personally, that its light can end its long journey in your eyes, is a reminder of the bridge that exists between human scale and cosmic scale. We are not separate from the universe. We are participants in it, receivers of its messages, interpreters of its history. So when we speak of Andromeda's size, we must also include this dimension of time. It is not only wide in light years, it is deep in years of light. Its immensity is not only measured across space, but across the history it carries in its glow. To see it is to see both distance and duration, both immensity and intimacy. What does it mean for us to live in the presence of such scales? How do we measure ourselves against a galaxy whose light has been on its way since before our history began? It is one thing to speak of galaxies in numbers and measurements, to describe diameters in light years, star counts in the hundreds of billions, masses in the trillions of suns. It is another thing entirely to ask what all of that means for us. We live on a planet that feels large when we walk its surface, that seems immense when we cross oceans, that seems endless when we fly across continents. We live within a solar system where the distances between planets can take years of travel for spacecraft. And yet, when we place ourselves against the scale of Andromeda, or of galaxies in general, our measures collapse. The vastness is so overwhelming that human scale becomes almost invisible, and yet, invisibility is not the same as irrelevance. To feel small is not to be unimportant. The human scale is different, not in competition with galactic scale, but in relationship to it. The Andromeda Galaxy exists on its immense scale, but we exist on ours, and our ability to perceive it, to ask questions about it, to send light and machines and thought into the cosmos is itself extraordinary. To place ourselves against the vastness is not to erase ourselves, but to locate ourselves, to find meaning in the contrast. Think for a moment about the numbers. The Milky Way contains about 400 billion stars. Andromeda may hold nearly 1 trillion. Our Sun is one among those billions. Around it, the Earth orbits at a distance of 150 million kilometers. That distance is immense compared to our daily lives. It takes light 8 minutes to cross it. A jet aircraft travelling at 900 kilometers per hour would take more than 20 years of continuous flight to reach the Sun. Already this feels far beyond our usual frame of reference, but set that against the 2.5 million light-years to Andromeda, and the scale is reduced to almost nothing. The solar system, the Earth itself, our bodies, our lives, all of them shrink into a speck, smaller than a grain of dust when measured against galaxies. This recognition can feel unsettling. Some respond to it with a sense of insignificance, as though human lives are meaningless in the face of such enormity. But another response is possible, one that is both truer and more sustaining. Smallness is not the same as meaninglessness. We do not measure the value of a flower by its size compared to a mountain, nor the value of a thought by its weight compared to a planet. Human existence has its own scale of meaning, one that is not diminished by the vastness of galaxies but framed by it. Our scale is the scale of experience, of perception, of consciousness. We can hold a thought about 1 trillion stars. We can imagine a distance of millions of light years. We can build instruments that capture the faint glow of Andromeda and translate it into data, into images, into understanding. No other species we know of has done this. The galaxy is immense, but our minds reach into that immensity, tracing it, questioning it, telling stories about it. That act of perception is itself an achievement, a kind of bridge across scales. It helps to remember that the atoms in our bodies come from stars. The carbon, oxygen, iron and calcium that make up our bones and blood were forged in stellar cores and supernovae. We are literally made of the same material as galaxies. The vastness is not only outside us, it is within us. The human scale and the galactic scale are linked by matter, by history, by the cycles of stars. To place ourselves against the vastness is to recognize that we are not separate from it, but part of it, expressions of the same universe on different scales. Consider the way we experience time. Human lifetimes are measured in decades. Civilizations last for centuries or millennia. Andromeda's light takes millions of years to reach us. Its stars live for billions of years. Its black hole has existed for more than 10 billion years. The timescales are different, but they are not alien. Our brief lives fit within the longer span, like moments in a longer story. To recognize this is not to feel erased, but to feel situated, to see that our time is one note in a symphony that began long before us and will continue long after. From another perspective, the human scale allows us to grasp what the galactic scale means in ways that are uniquely our own, A trillion stars is an abstraction, but when we think about our own sun, about the warmth it gives, about the life it sustains, we can extend that feeling outward, imagining countless other suns, countless other possibilities. The vastness becomes a stage for imagination, for curiosity, for wonder. In this sense, human scale is not in opposition to vastness. It is the means by which vastness becomes meaningful at all. When you stand outside and look at Andromeda, you're literally placing yourself against the vastness. You're a body a few meters tall, standing on a planet 12,000 kilometers across, orbiting a star in a galaxy of hundreds of billions of stars, looking at another galaxy with trillions of stars. The contrast is overwhelming, but in that moment the scales meet. The vastness becomes visible to human eyes. The human scale becomes aware of the galactic scale. That meeting is one of the most profound experiences we can have. Philosophers and poets have long reflected on this feeling. Some call it the sublime. The encounter with something so vast, so beyond comprehension, that it stirs awe and humility at once. Science gives us the tools to measure, to describe, to put numbers to the immensity. But the experience of standing against it remains deeply personal, deeply human. It is the same feeling that ancient stargazers must have felt when they saw the Milky Way stretching overhead, or when they noticed the faint blur of Andromeda without knowing what it was. The scale was the same then as it is now. Only our understanding has changed. There is also a practical side to recognizing our scale. When we measure ourselves against galaxies, we see how fragile our world is. The Earth is a thin shell of rock and water, a delicate environment within a vast cosmos. Galaxies will continue for billions of years, long after our sun has burned out. But our own survival depends on choices we make now, on how we treat our planet, on how we use the knowledge we have gained. The vastness does not diminish the importance of those choices. If anything, it magnifies them, reminding us that our fragile home is precious against the backdrop of stars. The human scale also gives meaning to the future of Andromeda and the Milky Way. The galaxies will collide in about 4 billion years. By then, the sun will be nearing the end of its life, the Earth perhaps no longer habitable. Humanity as we know it will be gone, though perhaps our descendants or the species that follow us will witness it. The collision will reshape the sky, filling it with streams of stars, eventually merging the two galaxies into one. From the perspective of the galaxies, this is simply a natural process. From the human perspective, it is a story of future skies, of what might be seen by beings yet to exist. The human scale turns a physical prediction into a narrative, something we can imagine, anticipate, even though we will never live to see it. To place ourselves against the vastness, then, is not to compare in terms of size or duration, but to recognize the relationship. Galaxies are immense, but our minds are capable of grasping that immensity. Our lives are brief, but they occur within a universe that continues. Our bodies are small, but they are made of the same atoms as the stars. The human scale and the galactic scale are not opposed. They are two ways the universe expresses itself. And so, as we continue our journey into Andromeda, we carry with us this dual awareness. We are small, yes, but not meaningless. We are brief, yes, but not without value. Our place is not at the center of the galaxy, but within it, as observers, participants, beings who can look up and ask what it all means. That act of asking, of seeking, is itself a form of scale, one that stretches beyond our size, beyond our lifespan, into the vastness we contemplate. Long before telescopes, long before the idea of galaxies existed, people looked up at the night sky and noticed a faint blur in the constellation we now call Andromeda. To them, it was not a galaxy, not a sprawling spiral of 1 trillion stars, but a mysterious patch of light. And yet they recorded it. They named it. They included it in their maps of the heavens. The story of Andromeda is not only a story of astrophysics, but also a story of human culture, of how generations of observers tried to make sense of what they saw long before the tools of modern science arrived. The earliest written record we have of Andromeda comes from the Persian astronomer Abd al-Rahman al-Sufi, who lived in the 10th century. In his Book of Fixed Stars, completed in the year 964, he described a small cloud in the constellation Andromeda. He called it the Little Cloud, noting its position relative to the nearby stars. His text was not the first time anyone saw it. People must have noticed the blur for thousands of years before, but it is the first surviving written account we can point to with confidence. Al-Sufi's book was part catalogue, part guide, and his description preserved the knowledge of Andromeda for future generations. It is likely that earlier observers also knew of it. The ancient Greeks mapped the constellation of Andromeda itself, tying it to their myths of the princess chained to a rock rescued by Perseus. The constellation includes the bright star Alpheratz and the chain of stars stretching across the sky. The faint blur that we now know as the Galaxy lies within this pattern. While we have no surviving Greek texts that explicitly mention it, the possibility is strong that they noticed it, even if they left no record. The faintness of Andromeda makes it easy to overlook, but for careful observers under dark skies, it would have been visible. In other traditions, the blur may also have been noticed and woven into star lore. Indigenous cultures across the world have long traditions of sky watching, seeing patterns, shapes, and stories in the stars. Some Native American groups, for instance, describe the Milky Way as a path or a river across the sky. It is not hard to imagine that the faint blur of Andromeda could have been seen and given a place in such cosmologies, even if those records have not survived in the written form that reached us. By the Middle Ages, Andromeda's blur had entered European astronomy through translations of Arabic texts. Al-Sufi's Book of Fixed Stars influenced scholars across the Islamic world and then into Europe, where the little cloud became part of the celestial maps used by astronomers. To them, it was still just a nebula, a term used for any faint cloud-like object in the sky. The word did not carry the meaning it does today. It was simply a description, a cloud, a patch, a blur. For centuries, Andromeda remained in that category, catalogued but unexplained. The invention of the telescope in the early 17th century changed everything. With lenses and mirrors, astronomers could magnify the sky, bringing faint objects into sharper view. In 1612, the German astronomer Simon Marius observed the Andromeda Nebula through a telescope. He described it as a faint cloud-like light, larger and more distinct than could be seen with the naked eye. He's often credited with the first telescopic description, though it is possible Galileo also glimpsed it. Still, even with telescopes, the true nature of Andromeda remained hidden. It was still considered nebula, thought to be a cloud within our own galaxy. Over the following centuries, Andromeda's place in catalogues grew. Astronomers such as Charles Messier, who compiled a list of fuzzy objects to avoid mistaking them for comets, included it. In his catalogue it became Messier 31, or simply M31, the designation it still carries today. William Herschel, who discovered Uranus, also studied it, describing its bright core and extended faint regions. Some astronomers speculated that these nebulae might be distant systems of stars, but the idea was controversial. The prevailing view held that the Milky Way was the entire universe, and that nebulae like Andromeda were simply parts of it. The debate reached a turning point in the early 20th century. Astronomers such as Heber Curtis argued that spiral nebulae were island universes, galaxies in their own right, far beyond the Milky Way. Others, like Harlow Shapley, disagreed, insisting that the Milky Way encompassed everything. This debate culminated in the famous Great Debate of 1920, held at the Smithsonian in Washington, D.C. The question of Andromeda's nature was at the heart of the discussion. Was it part of our galaxy, or was it a separate galaxy of its own? The answer came only a few years later thanks to Edwin Hubble. Using the 100-inch Hooker telescope at Mount Wilson Observatory, Hubble identified Cepheid variable stars in Andromeda. By measuring their brightness and pulsation periods, he determined their distance. They were far too distant to be part of the Milky Way. Andromeda was a galaxy of its own, millions of light years away. With that discovery, the universe suddenly expanded. The Milky Way was no longer the whole cosmos. It was one of countless galaxies, and Andromeda was our nearest neighbour. Looking back on this history, it is remarkable to think how long humanity lived with Andromeda as nothing more than a faint blur, a little cloud noted in passing. For 1,000 years after Al-Sufi, it remained mysterious. Only in the last century did we learn its true nature. That transformation in understanding is one of the great shifts in human knowledge. The galaxy itself did not change. What changed was us, our tools, our concepts, our willingness to question assumptions, and the names reflect this history. From Little Cloud to Andromeda Nebula, to Messier 31, to Andromeda Galaxy, the object has carried labels that trace our growing comprehension. Each name marks a stage in the story, first a cloud, then a nebula, then a catalogue entry, and finally a galaxy. Even now, when we speak of it simply as Andromeda, we carry those layers of history in the word. The fact that people noticed it at all speaks to human attentiveness. It is faint, easy to miss. Yet under dark skies, generations saw it and wondered. They gave it a place in their maps, their myths, their catalogues. They preserved it for us, passing it down so that when the tools arrived to reveal its true nature, the object was already known, already marked in the sky. Without that continuity, Hubble might not have known where to point his telescope or what questions to ask. The faint blur in the constellation of a chained princess became the key to unlocking the immensity of the universe. When we place ourselves against the vastness of Andromeda, we are not only looking outward, we are also looking backward into the history of human observation. We are participants in a lineage of stargazing that stretches from ancient storytellers to medieval scholars to modern astronomers. To see Andromeda is to join that lineage, to continue the act of noticing, of naming, of wondering. If you could stand beneath a perfectly dark sky, far from the glow of cities, Andromeda would appear to you as a faint smear of light, barely there, just on the edge of vision. For thousands of years, that was all humanity could see of it. A little cloud, a blur in the night. But with the invention of the telescope and later with the rise of giant observatories on mountaintops and in space, the faint blur has been transformed into a galaxy alive with detail. Modern telescopes have revealed Andromeda not just as a patch of light, but as a sprawling spiral of stars, dust and gas, a living system full of complexity. When Edwin Hubble turned his telescope on Andromeda in the 1920s, he could identify individual stars for the first time, and that breakthrough proved it was a galaxy beyond our own. In the years since, the tools have grown enormously in power. The Hubble Space Telescope, launched in 1990, has taken some of the most detailed images of Andromeda ever captured. Its cameras have resolved millions of individual stars within the galaxy, something ground-based telescopes could never achieve with the same clarity. In 2015, a mosaic of Andromeda created with Hubble data stunned the world. It showed a 1.5 billion pixel panorama, each tiny point a star, filling the spiral arms in detail so fine that it seemed almost endless. That image remains one of the largest astronomical photographs ever made, and it gave us our first true sense of the galaxy's immensity on a human scale. But Hubble is only one piece of the story. Telescopes that see in other wavelengths have opened windows onto aspects of Andromeda invisible to ordinary eyes. In infrared, instruments like the Spitzer Space Telescope and the Herschel Space Observatory have shown the galaxy's dust glowing warmly, tracing out rings and arcs that reveal past interactions with companion galaxies. These structures are invisible in visible light, but in infrared they shine clearly, evidence of waves of star formation triggered by gravitational encounters. In ultraviolet, the Galaxy Evolution Explorer, or GALEX, revealed Andromeda's population of hot young stars, highlighting regions where new clusters are forming. Ultraviolet light does not travel well through dust, so these views emphasize the areas where gas has recently collapsed into stars, where the galaxy is actively renewing itself. The contrast between infrared and ultraviolet images is striking. One shows the raw material, the other shows the result. Together they tell a story of constant cycles of birth and death. In X-rays, telescopes like Chandra and XMM Newton have observed the remnants of exploded stars and the activity around Andromeda's central black hole. These high-energy views highlight the violent processes that shape galaxies from within. Supernova remnants glow in X-ray light, vast shells of gas expanding into the interstellar medium. Binary star systems, where matter from one star spirals onto a compact companion, flare brightly. The black hole itself is faint but detectable, a reminder of the extreme forces at work at the galaxy's core. Radio telescopes add another layer. By tuning to the 21-centimetre line of neutral hydrogen, astronomers have mapped the distribution of gas in Andromeda, showing how it extends far beyond the visible disk. These radio maps reveal structures that are otherwise invisible, stretching the galaxy's size and showing how gas flows within it. They also provide crucial evidence for dark matter, because the rotation speeds of the outer gas cannot be explained by visible stars alone. Without radio telescopes, our picture of Andromeda would be incomplete, limited to what starlight can show. The power of modern telescopes is not only in their ability to see in different wavelengths, but also in their ability to combine perspectives. When data from optical, infrared, ultraviolet, X-ray, and radio telescopes are overlaid, Andromeda transforms into a multi-layered object, each wavelength adding detail, each revealing processes invisible to the others. The result is a portrait not of a static galaxy, but of a living one, full of cycles and interactions. Ground-based observatories have also advanced. Telescopes with adaptive optics can correct for the blurring effect of Earth's atmosphere, giving them clarity once reserved for space telescopes. Instruments on mountaintops in Chile and Hawaii have captured exquisite images of Andromeda, resolving star clusters, tracing dust lanes, and measuring motions of stars with precision. Surveys using wide-field cameras have mapped its halo, detecting streams of stars torn from smaller galaxies. These discoveries have shown that Andromeda's story is one of constant change, of growth through mergers, of a structure shaped by countless interactions. Modern telescopes have also allowed astronomers to look not just at Andromeda as a whole, but at its components in extraordinary detail. Star clusters, globular and open, have been catalogued by the thousands. Individual stars have been studied for their composition and age. The motion of stars within the galaxy has been tracked, providing clues to the distribution of dark matter. The Andromeda we know today is not just a blur, it is a detailed map, a system rich with data, studied from the broad sweep of its spiral arms down to the properties of individual stars. One of the most striking achievements is the realization that Andromeda's halo, the diffuse cloud of stars and dark matter that surrounds it, extends far beyond what we once thought. Observations have shown that its halo may stretch across millions of light-years, overlapping with the halo of the Milky Way. This discovery has profound implications for the eventual collision between our galaxies, suggesting that their outer reaches are already interacting long before their disks meet. Such insights are possible only with the sensitivity and scope of modern instruments. The images themselves carry a kind of quiet power. To look at a high-resolution photograph of Andromeda is to confront the immensity of it directly. Millions upon millions of stars, each resolved as a point, fill the frame. It is a visual representation of numbers that are otherwise abstract. You can see the crowding in the bulge, the arcs of the arms, the dust cutting across them. It becomes real in a way that words and numbers cannot fully capture. Modern telescopes give us not just data but vision, a chance to truly see our neighbour as it is. And yet, for all this progress, there is still more hidden. Even the best telescopes cannot reveal every detail. Andromeda remains partly mysterious, partly beyond reach. Future instruments, such as the James Webb Space Telescope, promise even deeper insights, with the ability to peer into its star-forming regions, to study its oldest stars, to trace its history with unprecedented clarity. Each new telescope adds a layer, sharpening our view, deepening our understanding. But the galaxy itself always retains more to discover, more to reveal. It is humbling to think how far we have come from the days when Andromeda was a faint blur called the Little Cloud. Now we can map its arms, count its stars, trace its streams, measure its black hole. And yet the blur remains. To the naked eye, Andromeda still appears as it always has, a faint patch in the sky. Modern telescopes have changed our understanding, but they have not changed the experience of seeing it. That experience remains as ancient as it is modern, as mysterious as it is measured. When you look at Andromeda, faint in the sky, it feels impossibly distant. 2.5 million light-years separate us, a gulf so wide that even light takes millions of years to cross it. And yet, despite that distance, Andromeda is not standing still. It is moving toward us. The measurements are precise. The galaxy is on a slow but steady journey in our direction, a journey that will end in collision. It is not a matter of if, but when. Astronomers can already trace its motion, predict its path, and sketch the outlines of what the future will look like when the two largest galaxies of the local group finally meet. The evidence comes from light itself. When we measure the spectrum of Andromeda, we see that its light is slightly shifted toward the blue. This blue shift means it is moving closer to us, compressing the wavelengths of its light as it approaches. Most galaxies in the universe are redshifted, receding from us as space expands. Andromeda is one of the few major galaxies coming nearer, its local gravitational relationship with the Milky Way, overwhelming the general expansion of the cosmos. Its speed is about 110 kilometers per second in our direction. That may sound fast, but across millions of light years, it is a slow drift. The collision will not occur tomorrow, nor in human lifetimes, but in about 4 billion years. To picture what such a collision means, it helps to clear away certain misconceptions. Galaxies are not solid objects. They are mostly empty space, with stars separated by distances so vast that even in a collision, the chance of two stars physically striking each other is almost non-existent. Instead, what happens is more subtle, more grand. The gravitational fields of the galaxies interact, pulling and stretching them, distorting their shapes, sending stars onto new orbits. Gas clouds collide and compress, triggering waves of star formation. Over billions of years, the two spirals merge into a new galaxy, a single, larger structure that blends their stars and dark matter into one. Astronomers have simulated this future using powerful computers. In these models, Andromeda and the Milky Way approach each other slowly, their halos overlapping first, then their disks interacting. On the sky, Andromeda would grow larger and larger over millions of years until it dominated the view, no longer a faint blur but a vast presence. When the galaxies first passed through each other, tidal tails of stars would be flung outward, great arcs stretching into space. Over time, the galaxies would fall back together, their motions spiraling inward until they coalesced. The final result would not be a spiral galaxy, but a giant elliptical, a new galaxy sometimes called Milkomeda, a name that combines both. For Earth, the collision will be both dramatic and gentle. Dramatic because the night sky will change profoundly. The familiar stars of the Milky Way will be joined by streams and arcs of stars from Andromeda. Over generations, the view will become crowded, filled with features unlike anything we see now. Gentle, because the vast spaces between stars mean our solar system is unlikely to collide with another star. Instead, we may simply be carried into a new orbit within the merged galaxy. Our position shifted, but our system intact. The true violence will be felt in the gas clouds, where collisions will ignite new waves of star formation, lighting up the merger with fresh brilliance. The collision will also involve the central black holes of both galaxies. Each one will spiral toward the other, losing energy through gravitational interactions until finally they merge into a single, even larger black hole. This event will release gravitational waves, ripples in space-time that spread across the universe. Though we will not be here to witness it, future beings, perhaps in other galaxies, may detect those waves as evidence of the merger that reshaped our local group. Thinking of this future shifts our sense of time. 4 billion years feels impossibly far. Human history is measured in thousands of years. Civilizations rise and fall in centuries. Our species itself is only a few 100,000 years old. And yet, 4 billion years is the span of Earth's history so far, from its formation to the present. To think forward that far is to imagine timescales on which continents shift, oceans form and disappear, stars live and die. It is not so much a prediction of what humans will see as it is a recognition of what galaxies do, of how the universe evolves across immense spans of time. There is a kind of comfort in this. The collision is inevitable, but it is also slow, unfolding so gradually that no single moment will be catastrophic. Stars will continue to shine, planets will continue to orbit. The galaxies will dance together for billions of years, their structures blending in slow motion. For anyone alive to see the early stages, the view of the sky will be transformed, but not in a way that brings destruction. It will be a spectacle, not an end. Andromeda's journey toward us is a reminder that the universe is dynamic. We often picture galaxies as fixed, eternal objects, but they are always moving, always interacting. The Milky Way itself has grown by merging with smaller galaxies, absorbing their stars into its halo. Andromeda has done the same. Their coming together is simply the next step, a natural part of galactic evolution. In the larger cosmic web, clusters of galaxies merge into larger clusters, superclusters stretch and shift. The universe is always in motion, and we are part of that motion. When we place ourselves against this future, we find once again the contrast between human time and cosmic time. To us a collision is sudden, dramatic, violent. To galaxies, it is slow, patient, almost serene. The language of motion changes at these scales. What feels like inevitability to us is just one frame in the universe's ongoing story. Andromeda's journey is not a catastrophe in waiting, but a transformation in progress, one that will reshape the local group into a single, larger galaxy. The idea that the faint blur you see in the sky is on its way toward us adds another layer of meaning to its light. Those photons began their journey millions of years ago, when Andromeda was slightly farther away. Each night new light arrives, carrying the message that the galaxy is still coming, still drifting closer. It is as if the universe is reminding us, night after night, that change is always on the horizon, even if the horizon lies billions of years ahead. To contemplate this journey is to glimpse the scale of cosmic patience. The collision will not rush. It will not arrive unannounced. It is unfolding already, slowly, inevitably. The galaxies are bound by gravity, their paths drawn together, their futures entwined. In that sense, the meeting is not in waiting at all. It has already begun. From here, it becomes natural to wonder what the view will look like when the collision is underway, what will fill the skies of future Earth, or whatever worlds may exist then. What will the merging galaxies appear like to any beings who might stand beneath their light? To imagine what the future merger of Andromeda and the Milky Way will look like is to step into a timescale far beyond our usual sense of history. 4 billion years from now, the sky above Earth, or whatever world humanity's descendants may call home, will be unlike anything we can currently see. The familiar band of the Milky Way stretching across the heavens will be joined, then reshaped, by the arrival of Andromeda. What we now know as a faint blur on the edge of vision will grow into one of the most dominant features in the night sky, changing slowly but inexorably over millions of years. In the early stages, long before the galaxy's touch, Andromeda will simply appear larger. Night after night, year after year, it will drift imperceptibly closer, its faint oval expanding until it rivals the moon in apparent size. To the naked eye of future observers, it will no longer be a subtle cloud but a sprawling structure, its spiral arms visible in detail without a telescope. Imagine looking up and seeing not only the familiar Milky Way but also another spiral galaxy hanging across the sky, its arms stretching wide, its core glowing bright. The sight would be breathtaking, a reminder of the scale of the cosmos written directly onto the canvas of the night. As the galaxies approach, gravitational interactions will begin to distort them. Their shapes will warp, their arms stretched into tidal tails that arc across space. To observers on Earth, or on any other world in the system, the sky will become crowded with new patterns of light. Great streams of stars will appear, arcing across the heavens, shifting over thousands of years into forms no human eyes have ever seen. The galaxies will not remain perfect spirals. They will become stretched, elongated, twisted by each other's gravity. When the disks finally overlap, the view will become even more dramatic. The sky will be filled with overlapping clouds of stars, two galaxies mingling in sight as well as in structure. The Milky Way will no longer be a band of light, but a chaotic tapestry of overlapping arms, bulges and streams. To those who witness it, the night will never again be dark. Everywhere they look, stars will fill the sky, brighter and denser than anything we see today. And yet, as dramatic as it looks, the process will be gentle on the scale of individual stars. The chance of our sun colliding directly with another star is vanishingly small. Stars are simply too far apart, even in dense regions of galaxies. Instead, the drama is played out in the grand motions of billions of stars, shifted into new orbits, scattered across new paths. To observers, it will look like fireworks on the grandest scale imaginable, but to the solar system itself, it may simply mean drifting into a new part of the combined galaxy. The collision will trigger waves of star formation as gas clouds crash together. Future skies will be lit not only by stars already present, but also by countless newborn clusters, glowing blue with the light of massive young stars. Nebulae larger than any in our current galaxy will shine, regions of starbirth ignited by the compression of gas. These will appear as great glowing patches scattered across the sky, rivaling or outshining the Orion Nebula we see today. For beings alive then, the heavens will be alive with both old and new light. As time goes on, the galaxies will pass through each other and then fall back together, their mutual gravity pulling them into repeated encounters. Each pass will alter their shapes further, sending out new tidal streams, creating shells and arcs of stars. To observers, the sky will be in constant transformation, not from night to night, but from age to age. Generations would live and die under skies that change subtly, each seeing patterns their ancestors never knew. For them, the heavens would be a living thing, evolving across lifetimes. Eventually, after billions of years, the Milky Way and Andromeda will settle into a single, merged galaxy. Its structure will not be a spiral, but a giant elliptical, smooth and rounded, lacking the graceful arms that once defined them. From within it, the sky will be dense with stars, a glowing haze stretching across all directions. The familiar identity of the Milky Way will be gone, replaced by a new entity, sometimes called Milkomeda. For those who look up then, the night sky will bear little resemblance to ours, but it will carry its own beauty, its own story. To think about this future is to realise that the Andromeda we see today is only temporary. its spiral arms, its bulge, its satellites, all of it will be reshaped. The faint blur in our sky is not a permanent feature, but a phase in a much longer process. Our current view is just one snapshot, one stage in the dance of galaxies. The immensity of Andromeda is not only in its size, but in its destiny, in the role it plays in shaping the future of our local group. It is also worth remembering that this future will unfold whether or not Earth is still habitable. In 4 billion years, the Sun itself will be nearing the end of its main sequence life, swelling into a red giant, altering the conditions of our planet. Life as we know it may not survive, but perhaps other worlds will host observers who look up and marvel at the merging skies. Or perhaps humanity, in some evolved form, will have found new homes, carrying with them the memory of what the sky once looked like. The story of Andromeda's merger is not just a story of galaxies, but of perspective, of what it means to imagine the future of the cosmos. Computer simulations give us glimpses of what this future might look like. In visualizations, the galaxies drift closer, their shapes warp, their stars scatter into streams. Watching these simulations is like watching a time-lapse of billions of years compressed into minutes. They remind us that the universe is not static. The shapes we see in telescopes today are temporary, destined to shift and blend. The spiral elegance of Andromeda will one day be gone, but in its place will be something new, a testament to the ongoing creativity of gravity. For now, the merger is only a prediction, a vision of the far future. But the fact that we can predict it at all is remarkable. By measuring light, by tracking motion, by modelling gravity, we can see billions of years ahead. We cannot predict our own weather more than weeks in advance, but we can say with confidence that Andromeda and the Milky Way will collide. That certainty is a measure of how deeply we have come to understand the universe. And so, when you look at Andromeda in the sky, you're not only seeing what it was millions of years ago, you're also seeing what it will become. Its light carries both past and future, both memory and destiny. The faint blur is not static. It is a participant in a cosmic dance that will reshape the heavens. To know that is to see the galaxy not only as it is, but as it is becoming. Andromeda is not the only galaxy in motion, not the only one that merges, not the only one that reshapes itself through encounters. Across the universe, collisions are common. Galaxies grow by merging, by absorbing, by blending into new forms. What we see in Andromeda's future is a reflection of what happens everywhere, a process written into the very fabric of cosmic history. When we ask how big Andromeda really is, the question seems straightforward. We can measure its diameter, about 220,000 light-years. We can estimate its mass, perhaps 1.5 trillion times the mass of our Sun. We can count its stars close to 1 trillion. These numbers are staggering, but they raise a deeper question. Does size even mean anything at this scale? When we talk about galaxies, clusters, the cosmic web itself, our usual concepts of size begin to unravel. The numbers grow so large that they escape our intuition, leaving us with words and figures that we can say but cannot quite feel. On human scales, size is concrete. A mountain is larger than a house. An ocean is larger than a lake. Even the Earth, at 40,000 kilometers around, can be grasped with effort, because we can travel across it, see its curvature from space, measure its dimensions with familiar units. But a galaxy is something else entirely. A light year itself is already beyond our everyday sense, nearly 10 trillion kilometers. To say Andromeda is 220,000 light-years across is to speak of distances so large that we can only approach them through metaphor. Imagine light, the fastest thing in the universe, racing for a year without pause. That distance is 1 light-year. Multiply it by 200,000 and you have Andromeda's width. It is a number that resists being brought down to Earth. And yet, astronomers use the word size because they must. They need ways to compare, to classify, to describe. Some galaxies are dwarfs, only a few thousand light years across. Others are giants, stretching over 500,000 light years. Andromeda sits on the larger side, but not the largest. It is big enough to impress, but small enough to remind us that the universe holds still greater things. But what does it mean to compare? Does saying that one galaxy is twice as wide as another really capture anything about what it is like to exist inside them? In many ways, size in astronomy is shorthand. A galaxy's diameter tells us something about the extent of its disk, about the reach of its arms, about how much space its stars and gas fill. Its mass tells us about its gravitational strength, about how it pulls on satellites, about how fast stars orbit within it. But these numbers are abstractions, summaries of a complexity too great to convey in a single figure. When we say Andromeda is this big or that massive, what we mean is that it occupies a domain of influence, a space where its gravity dominates, where its stars belong. The number is a proxy for a reality far richer than any measurement. It is also important to remember that galaxies do not have sharp edges. The Milky Way, Andromeda, all of them fade gradually into halos of stars and dark matter. Where do you draw the boundary? At the edge of the visible disk. At the last star you can measure, at the point where its gravity weakens. Each choice gives a different answer. In that sense, even the number 220,000 light-years is an approximation, a convention rather than a firm boundary. Galaxies are fuzzy things, with edges that blur into their surroundings. When we ask about size, we're also asking about perspective. To an observer inside Andromeda, living on a planet circling one of its stars, the galaxy would feel both immense and invisible. The band of its stars might stretch across their sky, much as the Milky Way does for us. But they would not see the spiral shape directly. They would infer it, build maps, make models, just as we have done. For them, the galaxy's size would not be a lived experience, but a concept, a conclusion drawn from data. In that sense, the idea of size is less about reality and more about what beings like us can measure. This leads to another way of thinking about it. Perhaps at this scale, size is less important than structure, less important than relationships. Andromeda is not just 200,000 light-years wide. It is a spiral galaxy with arms, with a bulge, with a halo. It is bound in a gravitational relationship with the Milky Way. It has satellites, streams, a history of mergers. Its immensity is not only in how far it stretches, but in how it connects, how it interacts, how it evolves. Size is one measure, but it is not the only one, and perhaps not even the most meaningful. Consider too the role of time. Andromeda is not fixed. Its stars move, its arms shift, its satellites orbit. Over billions of years its shape changes. Its merger with the Milky Way will transform it entirely. If we try to fix its size as a number, we freeze it, but in truth it is always in motion, always in process. To speak of size at this scale is to take a snapshot of something that is alive in time, something that cannot be reduced to a single number without losing part of its essence. There is also the matter of relativity. Compared to us, Andromeda is immense. Compared to some galaxies, it is modest. Compared to clusters of galaxies, it is a speck. The concept of size depends on what you place it against. A galaxy is not large or small in itself. It is large or small in comparison, in relation, in context. To say Andromeda is big is to imply a perspective, a point of view from which it dwarfs us. From another perspective, it might be ordinary. Size at this scale is always relative, and yet for all these complications, the human mind continues to reach for numbers. We want to know how big, how many, how far. These questions are part of how we make sense of the world. They give us handles, ways to hold the immensity, even if imperfectly. To ask how big Andromeda is may not yield a simple answer, but it yields a path into wonder, into contemplation, into the recognition of how our categories stretch when applied to the cosmos. The very fact that we can ask the question is a sign of our curiosity, our desire to measure the unmeasurable. So perhaps the answer is that size does mean something, but not everything. It is a beginning, not an end. It is a way of pointing toward immensity, a way of naming the vastness without claiming to capture it fully. To say Andromeda is 220,000 light-years wide is to say, here is something immense, larger than you can imagine, but still part of the universe you inhabit. The number is both precise and inadequate, both useful and insufficient. When the night is quiet and the sky is clear, there is a moment when you can look up and remind yourself that you're standing beneath not only stars but galaxies. The Milky Way arches overhead, a river of light that comes from within our own home, and just off to the side, faint but present, lies Andromeda. To the unaided eye it is no more than a blur, a dim cloud among brighter stars, yet within that blur lies an immensity greater than our own galaxy, a trillion suns gathered into spirals and streams, drifting toward us across millions of light years. It is remarkable to think of how this faint smudge has carried such weight in human imagination. For centuries it was simply a mystery, a patch of light noticed, named, catalogued, but not understood. Then, with the advance of telescopes, it became a revelation, proof that the universe was larger than we had ever dreamed. And now, with modern instruments, we see it in detail, its arms traced with stars and dust, its halo stretching wide, its satellites clustered around it. We measure its mass, its size, its motion. We predict its future, the collision that will merge it with the Milky Way. The faint blur has become one of the most studied objects in the sky, a symbol of cosmic immensity and human curiosity. And yet, when you stand beneath it, none of those numbers are necessary. The experience of looking is enough, intellectually, that it is vast. It contains stars beyond counting. It is coming toward us slowly, inevitably. But in the moment of looking, it is simply there, a soft glow, a reminder that the universe holds more than we can see. It invites you to pause, to breathe, to let the scale wash over you without needing to solve it. The immensity does not demand understanding, it offers perspective. Falling asleep beneath such a glow is to carry that perspective inward, to let your mind drift on the scale of galaxies, to imagine their arms sweeping across space, their stars orbiting in endless patterns, their black holes anchoring their cores. To imagine Andromeda as it is now, as it was when its light began its journey, as it will be when it collides with us. The mind cannot hold all of it at once, but it can wander among the pieces, moving from stars to dust to halos to mergers, finding rest in the rhythm of immensity. There is something calming in knowing that galaxies move on timescales so long that our own worries, our own anxieties shrink in comparison. The things that trouble us in daily life feel urgent, immediate, pressing. But compared to the billion-year dance of galaxies, they are fleeting. That does not make them unimportant, but it puts them in perspective. To sleep under Andromeda is to let that perspective soften the edges of thought, to remind yourself that you are part of a universe that stretches far beyond this moment. Andromeda is not only out there in the sky, it is in here too, in the atoms of your body. The carbon, the oxygen, the iron, all were forged in stars like those that fill Andromeda. You're made of the same material, shaped by the same processes, carried by the same cycles. To reflect on that as you drift into sleep is to feel connected, not separate. You're not just looking at a galaxy. You're part of the same story, the same physics, the same universe that gave rise to it. The galaxy will continue long after you close your eyes, long after you wake, long after humanity itself is gone. Its stars will rise and fall, its arms will shift, its collision with the Milky Way will reshape it. But tonight, its light has reached you. Photons that left millions of years ago ending their journey in your eyes. That is enough. You are part of its story simply by seeing it, by knowing it, by letting it rest in your mind as you rest your body. So, as you lie down and let your breathing slow, imagine that faint glow above you. Imagine its arms stretching wide, its stars countless, its future immense. Let it remind you that you are small but not alone, that you are fleeting but part of something enduring, that the universe is vast, and yet here you are, able to feel it, to think about it, to find calm in its immensity, and as sleep comes, carry that glow with you, the glow of 1 trillion stars, the glow of a galaxy drifting toward us, the glow of the universe itself reflected in your quiet thoughts. It is not just light in the sky, it is a companion in the night, a reminder that even in the darkness there is always more beyond, always something greater, always a reason to look up, even if only in memory as you drift into dreams. Thank you for sharing this time beneath the stars. If you found calm in these reflections, you're welcome to return whenever you wish, to let the universe keep you company. If you'd like to hear more stories like this, you can always follow along and join me again the next time we drift through another mystery of science. For now, may your night be peaceful, may your thoughts be light, and may sleep come easily, carrying you gently into dreams.